All right. Thank you again. And Laura, you're up.
Thank you very much. So first of all, let me thank you very much, Stefan, for the organization of this workshop. It's super nice being here. I'm happy I made it. And yeah, I mean, yesterday was super nice. And I think today and the next days are going to be very nice too. So, okay, my talk is already going a bit broad because there's a little bit of a different flavor with respect to the one yesterday, in the sense that this talk is going to be about some matching games, which are like problems that arise in game theory. And I want to highlight some parts in which, for solving these kind of games, of analyzing them, then the concept of circuits can be, pops up, and so can be used. And then I also want to talk a little bit about some diameters, about polytopes that relates to these games. Okay, so first, let's start with saying a little bit what does it mean matching games. So there are several interesting game theory problems that somehow involve the structure of matching in graphs. I don't know how many of you are familiar, for example, with the very famous table matching games introduced in the seminal paper of Gayle Shapley, or cooperative matching games, again introduced by Shapley and Shubik, or more recently network bargaining games introduced by Klambert and Hardosh. But let's say instances of such games are somehow described by a graph where the vertices represent the players and the edges represent possible player interactions. And somehow the structure of matchings is involved in defining what is called the outcome. Okay, now what does all of this have to do with circuits? Where in this talk, I'm going to use the concept of circuits and diameter in the context of matching. So I will show that there is some part of some problems related to this, in which this concept actually pops up nicely. Okay, so it's going to have two parts. So in the first part, I will focus on network bargaining games and show that in some of the proofs of the results that we have, we use the concept of circuit. And then in part two, I'm going to look at stable matching games, and I want to talk a little bit about diameter of the associated polytopes. Okay, so we start with the first part. So network bargaining games and circuits. So first, I will have to define what a network bargaining game is, okay? And which are the problems that we are actually looking at here. So network bargaining games essentially can be traced back to the celeb work of Nash in 1950. So he investigated bargaining dynamics that actually was wondering how should two individuals agree on splitting the value of a deal. So suppose that we have two individuals here, A and B, and they could make a deal and earn $100 together. Okay, then how should these $100 be split? Now, one thing that we should take into consideration is that maybe not both individuals have the same interest in realizing this deal, because maybe they have some outside opportunities. So, for example, player A is an outside opportunities of $30, and player B is an outside opportunity of $50. So in order for them to decide to make a deal between themselves and leave out the outside option, clearly A should get at least $30 and B should get at least $50. And this is what is called a stable solution, because if A doesn't get at least this, then he will not be interested in making this deal. He would rather go to the outside option. And the same things with B. Of course, anything between 30 for A and 50 for B is stable, like they would agree on making this deal. But Nash also introduced the concept of somehow balanced solution, which is concept where kind of the revenue should be kind of fairly split among the players. So technically, each player should get at least the outside option, and whatever is more, like 20 will be more if we pay the outside option, then this should be fairly split among the two. Okay, now Kleinberg and Tardosh in 2008 introduced kind of a network extension of Nash problem. So instead of having just two players, here we have a network. And now the nodes represent the individuals, so we have a lot of them. links represent the deals of a certain value that the individual can agree on. And each individual entering the most one deal, and they have to agree on how to split the value. Exactly as before, okay? But now the outside option is implicitly given by the neighbors, and I will describe in a minute formally what this means. And still, the goal is to characterize existence of stable or balanced outcomes. In particular, stable, that means outcomes where people have no incentive to deviate. Okay, so long story short, we are given a graph, now connected graph, where nodes represent individuals, links represent deals of a certain value. We want to understand like how would individual agree in entering the deals, but we have to define what this outside option means, like how it is implicitly defined by the neighbors. Okay, so I'm going to do this a bit more formally. So we are given a graph G, and again, we have a weight vectors on the edges that represent the values of each deal. And the players, we said, that can enter into at most one neighbors. So essentially, an outcome at the end will consist of a part which is a matching that represent the deals that the players are making. But then, like if two players makes a deals, we have to agree on how they split the value. So we can represent this with an allocation. So essentially, it's a vector y that is telling me for every vertex, essentially, how much this vertex is getting, so this player is getting. So the allocation is to satisfy that for every edge in the matching that represent the deal that I'm taking, yu plus yv should be equal to this value because they have to agree exactly how to split it. Okay, and if a guy is not in any deal, then he should get 0. Okay, so does it make sense? So then an outcome for this game is a pair. I have a matching that represents the deals, and then I have an allocation that represents how I'm splitting these deals. Now, given an outcome, what is the outside option of the players? So for a given outcome, each player gets implicitly an outside alternative by looking at his neighbor. So I have a player U, right? This is the player U. And what I can do, I can look at my neighbors. So I have V1, V2, V3 here. And then I can look at what is, I mean, essentially among all my neighbors, okay, what is the maximum value of the deals that I could make minus what my neighbor is receiving. So what is happening now? So if you have a neighbor for you, so U is matched with someone somewhere, but maybe there is a neighbor B, okay, and such that whatever he is getting at the moment, YB, minus, I mean, if I subtract YV by the value of the deals, okay, if this is greater than what I'm currently getting, then actually player U has an incentive to break the current deal and get into a deal with V. Why? Because it could offer to V essentially what V is getting now, maybe just plus epsilon, but he would get something more. So if you have a neighbor in which this condition holds, then you would have an incentive to just break the current deal and say to V, hey, shall we go to a deal together? Both of us could get something more. Like in particular, I could give a very little epsilon more to V, and you can get something more than what is currently getting. Does it make sense? Okay, so essentially, if I give an outcome that is a matching and a Y, whenever these things happen, a player has an incentive to break the current outcome and make a deal with a node, with another neighbor. And so an outcome is called stable if this doesn't happen. And so this essentially translates into this condition that for all edges, yu plus yv should be greater than or equal to the value of the deal for the edge uv. So this is nothing but translating this condition, saying that this condition cannot happen. So this condition happens when yu plus yv is strictly less than wuv. Okay? Okay, so essentially, if you think about it, the values of the of the allocation should fractionally cover each edge to an extent of WUV. Okay, so one can further introduce the notion of balance outcomes, which is a generalization of Nash concept. So the values are also fairly split among the players. This is not too much important for this talk, but Kleinberg and Tartar does show that indeed, when you give the network bargaining instance, a balanced outcomes exist if and only if a stable outcome exists. So we can focus on stability. And this is true if and only if the graph is so-called stable. What does this mean? Well, a graph is stable whenever the natural LP relaxation for a matching problem has an optimal integer solution. So what is this? This is essentially the LP relaxation in which we have a variable for every edge. We want to maximize the weighted sum of the XE values. And we simply say that for every vertex, if you look at all the edges which are incident into the vertex, we can take at most one. So this is essentially the fractional matching LP. So what they prove is an LP characterization of instances that admit stable outcomes. So this all problem, network bargaining game instance, has a stable solution if and only if I look at this LP as an optimal solution that is integer. Does it make sense? Okay. Now, clearly, not all graphs are stable, and this can be clearly seen if you take just a triangle. Like if you take a triangle graph, then even if you have weights equals 1 to every edge, then an optimal solution of that LP is half for every edge, and maximum matching in that case will have a value of 1. So not all graphs are stable. And we know because that LP is too weak in general to describe matching, we need to have the outside inequality. So there are instances not admitting stable outcomes. And so for this reason, several researchers in the past years have investigated so-called stabilization problems. So you want to modify the instance to make them stable via different graph operations. And we can discuss a lot of which kind of graph operation could make sense from a game theory point of view. But one that I found particularly interesting is so-called vertex removal that corresponds to block some players. So maybe you have an instance, you realize that this instance is not stable, so it doesn't admit any stable outcomes for the network bargaining game. So essentially then the problem becomes, can we efficiently find a minimum cardinality set of players block, like to remove, such that G minus S is stable? And so is the optimization problem clear? And now one of the reasons why I like this is that this turned out to be polynomial time solvable. In particular for unit weight instances, this was first proven independently by Ito Katamura, Kamiyama, Kobayashi, Okamoto, and by Ahmadian, Hossein-Zadeh, and myself in 2017. And then later, actually with Cedric, we generalized these results to network bargaining instances in which we can have arbitrary values for the deal. Okay, so far so good. That's the this kind of the situation here. So what I want to move on is instead something that is another generalization. I mean, generalization of it in which we have capacities for the nodes. So in particular, Bateni et al. Introduce a generalization where each player is allowed to enter in more than one deal. So why each player should be restricted to enter in one deal? Maybe each player could enter in several deals with the neighbors. So again, we can represent this as an instance given by a graph, edge weights, and now we have an integer node capacity vector telling me for every player how many deals it can enter with. Now again, it's very similar to the unit capacities. An outcome is now associated with the so-called C matching. So is a bunch of edges with the property that if I look at any node, the sum of the edges that I'm taking should be less than or equal to CU, so the capacity bound. And now I also have an allocation because for every edge I have to decide, I mean the endpoints of every edge have to decide how to split. But the concept of outside option, a stable outcome, easily extend to this more general setting. So you can extend this notion. And indeed, Bateni et al. Show that also in this case, the LP characterization of stable outcomes generalizes. So a stable outcome exists if and only if the LP below, which is essentially the natural LP relaxation for the C matching, as an optimal integer solution. So again, here we just replace CV instead of 1 with respect to before. So this in general is a fractional LP. But if it happens that for your graph, for your instance, this is an optimal solution that is integer, then you will be able to have stable outcomes. And later, Farkazi, Georgius, and Kahneman also show that in this case, you can also compute so-called balanced solution, which is again where kind of the surplus of the values after the split. So given that this seems to be nice, it generalized from unit capacity network to capacitated network. It's kind of a natural question to ask what happened to vertex stabilization in this case. So if we have an instance that is does not admit stable outcomes, can we efficiently find a subset of players to block so that the instance will admit a stable outcome? Okay, so stabilization problems so generalizes to capacitated case, for example, in the following way. We're given a graph. We want to find the minimum cardinal set of vertices such that when I remove them from S, the graph becomes stable. But unfortunately, in a joint work with my student in particular, Matthew Gersten, who was a former student of mine at the University of Waterloo, and Lucy Verbeek, who is currently a PhD student of mine at UI Leuven. We actually show that vertex stabilization, unfortunately, becomes NP hard, and in particular, even hard to approximate within something better than this factor, which is something better than n to the power of 1 minus epsilon for any epsilon greater than 0. So essentially, like there is a very trivial ON approximation that you can just remove all the vertices, or maybe just leave whole vertices but 2. Then you have just a graph which is an edge, and that is clearly stable because a maximum matching will be integral. And essentially, this is saying that hoping to get something better than that, it's not possible unless P is equal to NP. Okay, and hardness holds even with unit edge waves. So the moment, with the results with Cedric before were showing that if you have arbitrary deals or unit weight deals, everything is still polynomial time solvable. But if you have higher capacity rather than 1, this instead makes the problem, difficult. No, so you
cannot split just the vertex to create copies.
No, you cannot split a vertex to create copy because so for 2 reasons. The first reason is that, but how I define this, you either remove a vertex entirely or not. So if you split and you try to apply the unit, you might remove partially. And we are going to that, so keep the question bento because you can repeat it now. Because then we're kind of looking at it and say, okay, what is that is making the problem so hard by just by introducing capacities? And actually realize that indeed we can have also another ways in this could generalize. So instead of completely remove a node or not, we could ask to decrease the capacity of a node. So essentially, vertex stabilization via capacity reduction. Like we are given an instance, we want to find a new capacity vector such that this is stable. We should have tilde. And such that the one norm of this vector is minimum. So essentially, we are just reducing as much as we can, or as little as we can, the capacity of every node so that the graph becomes stable. Does it make sense? But now one thing, just to again go back to Bento, you have to be careful when you do the splitting. Because when you do the splitting of the nodes, since you have that the edge are between 0 and 1, like you cannot just do an arbitrary splitting because you might end up in a situation in which your matchings will take twice the same edge. So if you have 2 nodes with capacity 2 and you split, you might take matchings twice the same edge. So that's also kind of not going as we want. But with Lucy, we could show that this vertex stabilization is now polynomial time solvable. So which is kind of what we were expecting. Okay, we understood that taking things in blocks makes the things hard, but when it just reduces the capacity, looks a little bit more similar in the 0-1 case. because if the capacity is 1, removing a player is also like reducing the capacity from 1 to 0. And so this is now polynomial time solving. And okay, I just want to mention that this is going to appear in the IPCO together with some other results, but this is something we realize later after that. And okay, so a few more things about this. So how is this kind of result proved, or what does it rely on? So it is well known that extreme point of the fractional C matching LP are half integral. So if you look at the LP relaxation, which we would like to have an optimal integer solution, then the LP relaxation is half integral. So the support will be a bunch of edges, which have a value 1. So it's a C matching. So I could have something like this. And then I might have some fractional values, but these fractional values, they need to form odd cycles. And these fractional values will always be 1/2. So extreme point solution of this LP over here, they are going to look something like this. I have fractional odd cycles and a bunch of edges. Okay. Now, for a given instance, let's denote by gamma the minimum number of odd cycles in the support of any maximum fractional C matching. So, I mean, if I have an instance, like, for example, if this is my graph, assume that all the weights are integer, are unit. Then if I look at a maximum fractional matching, so an optimal solution in which I maximize 1 transpose X, I could get, for example, that this is an optimal solution in which this value 1/2. So this is a value of 3, and I cannot get anything better than that. But here I also have this as a solution that has value 3, and this solution, like here, I only have integer values. So in this case, actually, this graph is stable, and in this case, gamma is a 0. Like I have an optimal solution with 0 odd cycles, but I could have some instances where that are not stable. So for example, if I just have a triangle, and so in a triangle, then clearly this gamma is 1, because I only have one optimal solution, which is giving 0.5 on each of these edges, and I'm going to create 1 odd cycle. So gamma is the minimum number of odd cycles that I have in any support of a maximal possible fractional C matching. So this is essentially optimal solution of the LP. And the main results that drive all the algorithmic results about vertex stabilization is this. Is showing that if you have an instance which is not stable and you take any vertex, if you remove the capacity, if you decrease the capacity by 1, then you are going to get a minimum number of odd cycles, which is at least the minimum number of odd cycles that you had before minus 1. So essentially what this is saying is that if you decrease the capacity of one vertex, you can decrease the number of odd cycles by at most 1. It cannot happen that you decrease the capacity by 1 and suddenly all your odd cycles disappear. So this is a main lemma that was holding already in the uncapacitated setting. So first proof for the uncapacitated unweighting, then proof from for the uncapacitated weighted, and now we proved this also for general capacities. And once you have this, then the algorithm becomes quite simple. You compute a fractional C matching with minimum odd number of odd cycles, and this is a general. I mean, we can do this for capacitated matching, generalizing an algorithm that Cedric and I we had for the uncapacitated one. And then if you compute this, then this lemma tells you that you need to decrease the capacity of at least one node for each cycles that you have. Then you can essentially decrease the capacity for one vertex for each cycle, and you are done. So once you have this lemma, This is telling you that you can stabilize distances by just looking at this minimum odd number of odd cycles, and for each of them, you can decrease the capacity by 1. Does it make sense? Now, the things that I want to show is that we're going to prove this, particularly for unit weight instances, exploiting the concept of circuits. So just to put things in context, so this lemma for the uncapacitated and unweighted case, when you have unit weights, it's quite easy to prove. Could prove it combinatorially. Then in the paper with Cedric, we look at still uncapacitated but weighted distance, and we had to prove this, but the proof was kind of more involved. And what I'm going to show now is that we can have a reasonably easy proof of this if we relies on the concept of circuits and actually edge walk on the polytope. So that's going to be the connection. Okay, so essentially, once again, okay, so let's reset it. We want to prove that if you look at optimal, maximal solution of that LP, of the fractional matching LP, optimal solution of the fractional matching LP have a bunch of edges and a bunch of odd cycles that are fractional, that have a value of 1/2. And so we want to show that, in the best case, if you reduce the capacity of one vertex, the minimum number of odd cycles can decrease by 1, but not more than that. Okay, so to exploit circuits, we have to go back to the circuits for the fractional matching polytope. And now, after yesterday's talk, they're very familiar too, because they have been discussed both in Jean talks and in Bento's talk. So in particular, if you remember, the circuits of the fractional matching polytope had a nice graphical characterization. So we had even alternating path or alternating cycles, and then we have things involving odd cycles. So we had either 1 odd cycles or 2 odd cycles, or 2 odd cycles joined by the path, or 1 odd cycles joined by path. I mean, I could have defined just these 2, to be honest, and say that the path could be empty, but just to make it clear, I put this a little bit like this to highlight the difference into the numbers here. But these are the circuit of the fractional matching polytope. And by now, you also know that the circuit do not depend on the right-hand side. So the fact that we are looking at the C matching, so that we have CU at the right-hand side instead of 1, doesn't change the set of circuits because they are completely independent. So these are the circuit of my LP. Okay, so now let's restate the main lemma for unit weight. So what we want that if I decrease the capacity of one vertex in my graph, can reduce the number of odd cycles by at most 1. So the minimum number of odd cycles that I have can go down by at most 1. So again, this is important because it shows that if you take the minimum number of odd cycles, you have to reduce for at least the number of these odd cycles. So then you reduce for 1 vertex on each of cycles and you are done. Okay, so how is this going to be related to the concept of circuits? So the proof idea can be by contradiction. So suppose that there is a vertex U for which you decrease the capacity, and suddenly, you have more than 1 odd cycle that disappears in an optimal solution of your LP. Okay, so let's consider the maximum fractional C matching that gives you this very little odd cycles. So here you have a number of odd cycles which is at least which has at least 2 less than the number of odd cycles that you had in the original graph. So you're removing the capacity of 1 node, and you have 2 odd cycles less or more. So let's consider this fractional matching that gives you this very little amount of cycles. Then we look at what happens to U. So essentially, we have decreased this capacity. We have a vertex U in which we have decreased the capacity. Now, in this matching, if somehow U belongs to a fractional odd cycle, then we can easily derive a contradiction in the sense that if we now, so this is my X, now assume that I'm increasing the capacity of U back, I'm increasing it to 1 by 1 more, then essentially what I can do, I can just go into a solution in which I kind of alternate the rounding here. So I take these two edge and I remove this. And if you was on a bigger cycle, this is all fractional. What will happen is it will be that if you increase the capacity back by 1, you can take this edge to an extent of 1, this edge to an extent of 1. You remove this, and you take this to an extent of 1. So if you do this operation, essentially you are essentially you can prove that this is again an optimal solution for your original instance, and this you even decrease even more the number of cycles. So that is not possible. So if you is in some odd cycles, then it's easy to derive a contradiction. This is not possible. So if U does not belong to any odd cycle, so when you reduce the capacity, then this is an extreme point solution for the graph that you obtain by decreasing the capacity, because U is not in any cycle, so it's easy to show that that is an extreme point. And so what is happening is that when you decrease the capacity, you are at an extreme point of the polytope. So if you put the capacity back, now, I don't know how my polytope looks like. So maybe you're here, okay? So what is happening now is that you have an extreme point solution that it is an extreme point for your original instance when you put the capacity back. But it might not, since it has very few cycles, it might not be, it cannot be optimum. So the optimum solutions had the minimum number of cycles, which is gamma. So for this extreme point here, since it has fewer cycles than gamma, then this cannot be optimal. But then what we know a lot about this polytope, and in particular, we know a lot how edge augmentation look like. This should be, I can move to an optimal solution that is somewhere here. I can move to an optimal solution from X to X star by doing a sequence of edge augmentation on the edges of the polytope. And I know, because we know very well how the edge direction looks like for the fractional matching, that in order for this to be augmenting, I need to move along a flower. Each flower is going to increase my objective function by a half. So I know that I am at most 2 steps away from the optimum. And this I know because I have an extreme point of my polytope. I'm not optimal because I have too few cycles, but I'm decreasing the capacity by 1. So essentially my objective function value went down by at most 1. Each augmenting direction will increase by at least a half because I can only go with the flower. So I am at most 2 steps away from the optimal. And so essentially what we can show is that, okay, so we are at most 2 steps away. And so we first have to move along the flowers, which is something like this. And then we need to perform another augmentation along the flower and some other flower. Then we can essentially then show that these 2 flowers, they need to intersect. So we take these 2 edge augmentation that we can have, and we can show that these 2 flowers needs necessarily to intersect. And if they intersect, then we can recombine them to either find an augmenting path that will lead me to an optimal solution in 1 step, or will lead me to find some augmenting structure that was already present in X. And so that would contradict the fact that X was a maximum fractional matching in the original graph. So long story short, like how is the proof based on sequence? We look when we reduce the capacity, where do we get in the polytope? So we get to a new extreme point, and in particular, we prove that this extreme point is at most 2 steps away from an optimal solution. And then we know a lot how these steps look like, because this is fractional matching, so it must be an augmentation that needs to use the flower, because everything is unit weights here. And so we can take these two flowers, we look at how they intersect, and we derive a contradiction to the number. So this essentially means that if you take this x is the distance 1 from on the polytope from the optimal solution. So you can create at most 1 cycle when you move through it. So that's essentially how things goes into play. Okay, and another thing that I also want to stress is that so once we have this, now going back to the algorithm again, the algorithm becomes quite simple. As I said, you need to compute a fractional C matching with the minimum number of odd cycles, and then you just decrease the capacity of 1 vertex for each cycle. And actually, just by talking to Cedric this morning, it made me realize that I should also mention that this is an algorithm, it's a combinatorial algorithm, but it starts from an arbitrary C matchings with a lot of odd cycles, and then decrease the number of odd cycles at each step until it arrives to one that has a minimum number of odd cycles. And this also has a polyhedral interpretation. So this algorithm is also an algorithm that essentially starts with an optimal solution of your LP, which is an extreme point, and moves to another extreme points of your polytope, right? By each time decreasing the number of cycles. So it is essentially an algorithm that walks on the edges of your polytope until you reach a fractional C matching that has the minimum number of cycles. So there is, so also here to prove this, and the extension that we have to do for C matchings is also an algorithm that can be interpreted as doing simplex moves or edge moves along the polytope. I mean edge, not simplex, because there is no kind of objective function, objective function defined. Okay, so that's one thing that I wanted to mention. And then the second part of the talk, I want to highlight some results related to stable matchings and diameters, and also that leads to some, in my opinion, nice open questions after. So what is a stable matching? So I don't know how many of you are familiar with the concept of stable matching. So in stable matching is defined as follows. We are given a bipartite graph. So it's a graph defined of two sets of vertices, let's say M and W, and a set of edges. And then, so each vertex in one set has a strict preference order over the individuals of the other set. So for example, here we have capital letters versus uppercase letters versus lowercase letters. So let's say that that this element here has a preference order over the elements in W. In particular, it would prefer small a over small b over small c, okay? And the same things for all the others. And what we would like to find, the matching that does not have blocking pairs. So what are blocking pairs? Where blocking pairs for a given matching are pairs such that M prefers W over its current match, and W prefers M over its current match. So there is some, for example, if we take this matching, okay, this matching is not stable. Why? Well, because this is a blocking pair. So capital A is currently matched to lower C, but it would prefer lower A to its current match. And lower A is currently matched with lower C, but he would prefer, again, lower A is matched with capital C, but he would prefer B over C. So both of them would rather be matched with each other than the current match that they have. And so this is called a blocking pair. So this is a matching that is not stable because these two individuals would rather be matched with each other instead of staying in the current situation. Okay? This has a lot of applications. I mean, you can imagine like students to university, when you do the application, you have your own preference for the university. The university has an own preference with respect to the students, maybe depending on the grades, or you can think about assigning students to supervisors for thesis, or you have hospitals and doctors where, like hospital might have preference depending on the specialty of the doctors. Doctors might have their preference depending on how close the hospitals are with respect to their home place and so on. So there is a huge literature about stable matching. And actually, so matching like this is stable, because you can see for every pairs that you don't have blocking pairs, because for every edge that you take notice the matching, either one of the endpoints would not want to switch. Okay, and edges like this, matching like this, are called stables. And actually, seminal papers of Shapley-Shubik, they show that Gayle-Shapley, they show that stable matching always exists, and they gave a very fast, actually linear in the number of edges, linear time algorithm that found the stable matching. It's a matching an algorithm based on proposal. It's super nice. But in general, stable matching are exponentially many in the graph, so there always exists at least one, but there could be a lot of them. And from an LP description, they are quite well understood. So in particular, there is a very nice LP description, see, for example, in the Bade paper. And the LP description is as follows. So the LP description is given by the following set of constraints. So the first two are essentially matching constraints. I'm looking at every M, and then say that if I consider, among all the edges, I have to take at most one because I want the matching. The same things I'm doing for W. If I consider all the edges, I want to select at most one because I want the matching. I have no negativity, so at the moment, these three are just the set of the matching constraints for a bipartite graph. But then there is this other set of constraints that actually tells you the following. Like, it tells you that for any edge, this edge should not be a blocking pair. So what does it say? It says that if I take any edge, MW, okay, either this one is in the matching, and I'm fine, or if not, it means that either if I look at W and I look at all M that she prefers over the current one, either W is matched with someone that they prefer, or it's M to be matched with someone that they prefer. So this is essentially the constraint. They're just saying for every edge, either it is in the matching or it cannot be a blocking pair, because one of the two endpoints is matched with someone better. And actually, the nice things about this is that this is all the inequality you need. So extreme point solution are in one-to-one correspondence with stable matchings, which is quite nice. And we also have bounds on the diameter of this polytope. So in particular, Erinikas, Magos, and Murtus in 2014 gave a top bound on the diameter. And this bound is n over 4, when n is essentially the number of nodes that are in the graph. Okay, so they proved this bound, and they also gave an instance where this bound is can be reached, can be attained. Okay, so far so good. We could also generalize this concept to stable matching with ties. So what happens is that this is defined exactly as the stable matching problem, but now in the graph that we have, in our bipartite graph, the order is not strict anymore, but I might have ties. Okay, so I still want the matching without blocking pairs, but now I have to be a little bit more careful. Blocking pairs is a couple of individuals that strictly prefer each other over the current match. So like in the stable matching, we said that every individual should have a strict order over the individuals of the opposite group. But for example, if you think about, I don't know, doctors and hospitals, maybe some doctors could be kind of indifferent between a couple of hospitals. Then should be one that he really wants, someone that really doesn't want, but maybe there are a bunch of them for which he's indifferent, and maybe the same things at the university. So allowing ties makes you model a lot more naturally some problems in which these order things are not strict. And okay. And but unfortunately, many things break down when you allow ties. And in particular, like in this case, the problems becomes difficult in the sense that for sure, a stable matching always exists. And why is this true? Well, because you could break ties arbitrarily and rely on the previous algorithm for stable matching. So if you break ties arbitrarily, then you are back to this to the strict ordering list, so you know that the stable matching rules exist. But now you might have actually stable matching of different size, of different cardinalities. So like before, everything is it goes pretty nicely. Now it doesn't go, things are more difficult. The particular NLP description is not known, and indeed optimizing over it is NP hard. It's almost like you don't have a nice description that you can handle with. So optimizing over it is NP hard because, for example, computing a stable matching of maximum cardinality becomes NP hard once you have ties. But we can still give a bound on the diameter of the polytope. And in particular, we are going to exploit the natural LP relaxation. So the LP that you've seen before, you can essentially just replace strictly greater than or equal to, because that is the condition that a blocking pair tells you. And so this now just gives you an LP relaxation. So you have fractional solution to this. But with a former student of mine, Felix Bachold, again from University of Waterloo, we could actually still prove a bound on the diameter, although we don't have the description of the polytope, right? But we could exploit the LP relaxation, and we prove a bound of n/3. And we also show that there are instances for which this bound is tight. And as a byproduct of our results, we show that also testing adjacency of two extreme points of this polyhedral can be done efficiently in polynomial time. And this is not always the case for polytope that are the set of feasible solution of hard combinatorial optimization problem. So if you look, for example, the TSP polytope, for the TSP polytope, you are able to give a bound on the diameter, but checking whether two extreme points are adjacent is hard. And instead, this is an NP-hard problem, but belongs to the class of problems for which testing adjacency on the polytope can be done in polynomial time. And again, a key point for this result, for giving a bound on the diameter, is to have a graphical characterization of adjacency of vertices on the polyhedral. And okay, so just quickly a few words on that. So a key component behind the diameter results for these problems is to have a graphical interpretation of adjacency of vertices. Like, again, vertices in the polytope corresponds to stable matching, so they have a graphical interpretation, they are matchings. So it's natural to try to understand if there is a graphical interpretation also of adjacency. When is that these two vertices are adjacent on the polytope? Do I have some graphical intuitions about it? And the answer turns out to be yes, for stable matching, and we generalize this with even in the case in which you have ties. So in particular, a key component is the so-called marriage graph, which is essentially a directed graph that represents your instances. So it's a directed graph like this, in which, I mean, essentially you have a node for every edge. So here, like how you should read this is simply as following. You have three elements in M, M1, M2, and M3, and you have four elements in W, W1, W2, W3, and W4. And you should read the edge by looking at the rows and the columns. So here you have essentially M1, M2, M3, W1, W2, W3, and this tells you the edges that you have. So you have M1, W2, and 1, W4. You have M2, W1, M2, W3, M2, W4. You have M3, W1, and M3, W2. So this is the graph. And this represents the preference list. So for M1, you look at the first row. And so the first row is telling you that W2 is preferred to W4. And to look at the preference of, I don't know, W2, you look here and you see that W2 is indifferent between M1 and M3 because it has these directed edges both ways. So a direct edge represents whether, like a directed edge like this means that if you go here, it means that for M1, M1 prefers W2 to W4. This direct edge, it means that for M2, M2 prefers W1 to W3, and so on. When you have a directed cycles, it means that they are indifferent. So this is the so-called marriage graph. And I mean, these are essentially what I said, the instance with the preference that you can reconstruct from here. And now just a nice thing is that given two stable matching, we look at subgraphs induced by particular set of vertices here. And okay, this is just an expression that might look complicated, but it's essentially rather simple. What this is saying is that if you have two stable matchings, like for example, you have a first stable matching, which is M2W1, M1W2. So this is M1W2 and M2W1. So this is the first stable matching. And this is another stable matching, which is M2W1 again, M3W2, and M1W4. So if these are my two stable matchings, I look at the subgraph induced by these nodes. And so in this case, it would be this, the subgraph induced. But technically, it's the subgraph induced by these nodes and also some other nodes if it happened that I had some other nodes in between these nodes that I select. So all of this is just to say that I could include in my subgraph nodes that are a little bit in between. But it's way more simple than now it looks like. But this is just saying that if I give two stable matchings and I look at the subgraph here induced by this particular set of nodes, then they are adjacent if and only if this subgraph contains only one non-trivial component. So in this case, I have one singleton component and only one component which is not singleton. So these two matchings are adjacent on the polytope. So this is a generalization of what was happening in the stable matching without ties. There is a stable, we have to tweak this definition here that for stable matching without ties is quite natural, but we need to tweak that. But the most, let's say, complicated things was to link subgraph or the marriage graph with the LP relaxation. So for stable matchings, you don't need to do that because stable matching are a distributive lattice, so it's easier at least to show that if you have more than one component, these are not adjacent by looking at some property of the lattice. We don't have a lattice, so we need to do some more work. So we have to identify inequalities of the LP by using horizontal and vertical paths on this marriage graph, and we kind of use them to show that I can find enough LP inequality that are tied for both. So even if this is just an LP relaxation, we can show adjacency for that. And then the diameter just follows by swapping each non-singleton component of them, and each non-singleton components involve the least 3 individuals, so you have at least number of individuals divided by 2. Okay, so long story short, I mean, I wanted to highlight, although we to convince this audience, but that studying circuits and diameter is useful and of interest beyond LP theory itself. So here I gave some at the beginning, like matching network games in which you have some algorithmic problem in which kind of you can use this concept to show something nice. And in particular, just to open questions, for stable matching, I not this graphical adjacency. Can we use them algorithmically? I think try to translate this into an algorithm, for example, to optimize an objective function over a stable matching. That would be super interesting if you're able to give an algorithm that is somehow exploiting this. And the other thing is that we have a diameter bound on the stable matching polytope, but what can we say about the circuit diameter? So again, I think this marriage graph has some potential to show something about circuit and probably like prove a better bound if we use circuit instead of edge. Yeah, thank you very much.
All right. Thank you. Do we have questions on Zoom? If not, then we'll move to the room.
So when you were taking away the weights of the vertex, your first matching one, how do you choose what vertex in that odd cycle to take away from?
That's a very good question. So let me repeat for the audience. So the question is, how do we choose the vertex from each cycle on which we want to decrease the capacity. So if I have unit weights, it doesn't matter. You can take any of them, you can reduce the capacity, and you will have a stable graph. And actually, even in the weighted case, you could take an arbitrary one, reduce the capacity, and you would have a stable matching. The only thing is that in the weighted case, so in the unweighted case, no matter which vertex you choose, you're going to decrease the maximum value of the matching by 1/2. In the weighted case, depending on which vertex you take, you might decrease the value of a maximum matching by more. So if you are interested in decreasing the minimum that you can, the value of a maximum matching, so in a way you want to stabilize the instance, but still players should get as much as it would be possible to get, then you can do that by taking the one that has the lowest dual value associated with it. So in the LP, the duals will assign some values on the nodes, and if you decrease the capacity to the one that has the lower value, you actually save at least 2/3 of the matching, and there are instances in which that's what you can get, and no more than that.
More questions? Yes, there's another one.
Does the result also hold C is arbitrary, real, non-negative, irrational?
Irrational. Quote Jesus here. So okay, so one thing. So first of all, okay, so one thing. So first, like arbitrarily big, or you cannot go because X is between 0 and 1. So anyway, you are bounded by N. So then if you have, so you mean if you don't have capacity which are not integer, then maybe you can break everything with an LP, because why would you decrease by integer? Then you would decrease continuously.
Yeah.
Then maybe you can just do that as an LP. Like you can model everything. Like if you don't have discrete decreasing, I think you could model this as an LP. Like, yeah. But I would have to check that, but I think that should work.
Does the nice characterization of basic solution still hold? C is not like half the different cycles. This would break, right?
So okay, so it will break the values that you. So it would break the values that they have, that they are not absolutely anymore, but it wouldn't break the support of how it looks like. So support would still look at odd cycle plus some edges, but then like the values in the odd cycle, they are, I mean, they are not necessarily after the none.
Yeah.
But the support is still the same, because like you're just changing the right hand side. So again, you don't.
This should still be okay.
Yes.
for the other.
Yes. Yes. Although again, for the algorithm that you don't decrease, like if you decrease by more than 1, or if you decrease continuously, then I think anyway, even without this, you might be able to write an LP.
All right. Okay, let's thank you for the nice talk again. Thank you. Welcome back, everyone. Next up, we have Johnny with a talk on, well, he will explain the topic to you.
So look, for reasons not beyond my control, I've changed the topic of the talk. I gave this talk 2 weeks ago to the day at ICERN, and some people were here, and I originally was going to give a different talk because I felt bad that those people at ICERN would hear this talk again, but I had to hear their talk twice. Here we go. So, but seriously, a little bit. The talk I was going to give, I don't need to talk about. There's a book to just read this book and get back to me. Okay, it's very yellow. It's a yellow book. I went with the yellow, but anyway, this is the talk I'm going to give. The talk is inspired, the title, by a graduate student here. How do I get rid of all this mess here? Do you know how to get rid of this?
I think we can hide the meeting control. Let me see. Okay, but I'm not good at moving the mouse here.
Yeah, so the book, the talk is about linear programming. It's not what I was going to talk about. I was going to talk about an interesting nonlinear discrete optimization problem that I realized after yesterday that nobody's interested in that kind of stuff here. So instead, I thought I'd talk more about linear programming and not, in general, but just some of my own personal observations, experiences. So what you're supposed to get out of this is certainly no advice whatsoever, no wisdom, just a little bit about, things that happened to me over the years. And it all kind of revolves around linear programming, maybe escape. There's that little mic.
Can you drag and drop?
Yeah. What if we just
You should just be able to drag it.
click on that thing? What if I click on that? What will happen?
That's what I did to minimize it.
Oh,
We
it's
still should
already-
move it around.
Yeah. Anyway, linear programming, Danzig gave this talk on linear programming, and this person named Hotelling stood up and said, well, the world's not linear, and sat down, and Danzig was shaking and all nervous, and somebody, came to his rescue. But this talk is a little bit about my sort of nonlinear path. And programming doesn't mean computer programming for Danzig, and planning. And you'll see my nonlinear path had nothing to do with planning whatsoever. So anyway, here we go. Oh, yeah, this was a picture I took of myself 2 weeks ago. Look, I look a little tense, right? Right? It's not, a lighthearted picture. So I just seen the aftermath of a car that had gone up on the sidewalk, knocked down some parking meters and a road sign. And, you sort of reflect a little bit about life in general when you see something like that. It just seemingly had just happened. And we'll come back to that. Anyway, let me take you back in time to 1978, actually. There's a picture of me on Live Slope at Cornell University. They kind of redid this, big donors, they put in this great rooms here, but there was this wall that I sat on, and I had no idea what was going to be coming, except I thought maybe someday I'd get some shoes. Anyway, I got my bachelor's degree in something called operations research and industrial engineering, but I avoided all the industrial engineering until recently. Now I'm in an industrial engineering department. But I stayed there and I got my PhD also. Some of you know some of the papers I wrote for my thesis. It was about circuits and oriented matrices. So it's about mostly about matrices that had determinants that were powers of 2, and what kind of matroids can you get from those matrices, what kind of oriented matroids, proximity results for IP for these kinds of matrices, how many columns can you have for a rank R matrix of that size. Nothing really much to do with optimization, but that was kind of something that was okay to do back then. So then I went to Yale Business School. Why would I go to Yale Business School? Well, my spouse was able to get a job near there. So okay, now I'm in a business school. This isn't actually the business school. This is the cemetery nearby. It says the dead shall be raised. And strangely, the one-way sign is pointing away from the cemetery, not into the cemetery. It seems like it should go the opposite way, but I was able to get out of there. But while I was there, I wrote some papers, as folks do. And here are some of the papers. So these 4 papers in particular, they're all over 30 years old now. They have a total of 18 Google Scholar citations, mostly self-citations. So this was not extremely popular work, but there was no Google Scholar back then. No one told me that I had to worry about people reading my papers. So I published in Math Programming and Math of OR. These journals still are pretty classy journals, and these are okay too. And yeah, over the years, it didn't get many citations whatsoever. So why am I talking about this? Well, it's easy to talk about new work that has no citations, or old work of other people often that has a lot of citations, but nobody wants to talk about their old stuff that never caught on, that had no impact on anybody. But it meant a lot to me. And so that's what I want to talk about a little bit at first here. So I wrote one more paper on this topic with my colleague, Jani. This, is not published. So you think yeah, that's the end of the line. We couldn't publish it anymore. But then we took out all the stuff that I had put in the paper, and then we published it, and it got lots of citations. So, I mean, that's why her name is first, not on the tech report, but on the actual published paper, because we took all my stuff out and she kindly let me stay on the paper. But, you know, so I'll tell you a little bit about this kind of stuff. But, you know, I just want to tell you, it's not that, you know, I didn't talk about this and try to advertise it. I give lots of talks at, you know, reasonable places on this material. You know, so it's not that nobody knew about it, it's just nobody liked it. So, but I went back to my alma mater, this is like 3 years after I graduated, to talk about this. And while this is going on, there's a lot of turmoil with that job, and that's what you have to appreciate. So, you know, I was basically losing my job. They were canceling my department of operations research at Yale University. So we were in the business school, we were this optimization group in the business school. There was kind of a political coup. We got kicked out of the business school. We were floating around this OR department in rented space. So all this is kind of going on. And I'm blithely writing my papers, you know, on polyhedral combinatorics and giving talks and trying to build my career. And so this is all kind of going on. There's a picture of us back then. This is the junior faculty in operations research at Yale back in these days. This is the late 80s. We thought this was rather funny. We were in rented space. We were about to be deleted. And so we took this picture. That's Janny Leung. She left, we all had to leave. So she left, went to University of Arizona. And then she went to Chinese University of Hong Kong. Now she's in Macau. That's me, believe it or not. That's my good friend Kurt Anstreicher. He's retiring this year. He was a student of George Danzig's. And this is Offer Kella. He's, you may not know him so well, he's at Hebrew University now. He's a probabilist. And his PhD advisor was Freddie Hillier of the book Hillier and Lieberman, the intro OR book. So there we were. It was good times. It was tough times. I think I'm wearing the same pants right now. But I did get smaller glasses. Anyway, so yeah, as I was saying, I went back to Cornell in '88. Like times were tough, but I went back to give this talk. And while you know, there I am back at Cornell. I think it was winter time. It is most of the time there. And you know, everybody's very interested in this material I was presenting. You know, I left there with my PhD. I'm talking about completely new stuff, and everybody was super interested in what I was talking about. But actually, Lou Valera, who was he was the person I took like graduate linear programming from. He said I should really talk to Alan Hoffman about this. So he didn't say he was interested, but he was like, well, this guy would really be interested. And this was really, you know, nice of him to tell me this. So I contacted Alan. Alan Hoffman was at IBM in the research division in Yorktown Heights, New York. I was at Yale. It's not so far. You'll see in a second if you're not familiar. So I contacted Alan. I don't know how I did it, like maybe a kind of a poll and turned a crank on I don't know, but in the late 80s, was there email? I think maybe there was a little bit of email. I think I had a little bit of email and I used that. Or maybe I called him on the phone. I have no idea. But anyway, I had to get there. MapQuest was only launched in 1996, so I couldn't use MapQuest. But I think I probably went and got like a paper map and figured out, you know, how to get there from Yale. It really wasn't too bad. So I set out for Yale. And Alan gave me the best mathematical compliment I ever received. He said, I was kicking myself when I saw what you did, meaning that he should have done it. And you think like, okay, you're a kid then. People will say that kind of thing to you many times over the years. No, it's still the best. So, you know, what I did, I'll give you some details of it in a second. I kind of connected polyhedral combinatorics and spectral graph theory for very symmetric polytopes. And I just kind of stumbled on it by doing some computation. So this harks to what Jesus said a little bit of, you know, do some computing and you may see something and it may lead you into some theoretical area. So, you know, Alan wouldn't have needed to do computing and frankly wouldn't have been capable of it. But that's another story. I taught him how to copy and paste. And he decided I was a computer expert because it was at IBM, let's say. But anyway, he was really an expert on these things. He was actually one of the people who founded this kind of polyhedral combinatorics approach to proving min-max theorems and And he knew a lot also about spectra of graphs, which just means eigenvalues of adjacency matrices of graphs. So anyway, yeah, I mean, Alan clued me in. So I'd written maybe 1.5 papers on this topic of those 4. And then Alan told me a lot more to go to this book of Benai and Ito, where I really learned, how all this stuff of spectral graph theory works and how to apply it to what I was trying to do. So let me give you a little bit of a picture of what that's all about. P is just, for us, it's going to be the convex hull of M points in Rn, and we're interested in the dimension of the polytope. If it's perfect matching polytope, it's not full dimensional. Traveling salesman polytope, directed or undirected, not full dimensional. So we're interested in the first step of analyzing a polytope, figuring out what its facets are. You want to figure out its dimension. So a good way to think about it is take all these extreme points and line them up in a matrix, put a column of 1s, and then just think a little bit about what does it mean to be an equation satisfied by all these points. And it just means that you're in the null space of this matrix. And then you just do a simple calculation using rank nullity theorem, and you see 2 different ways to think of the dimension. It's either n minus the maximum number of linearly independent equations for the polytope. Thinking about that linearly independent equations are just the coefficients or vectors in the null space of this matrix, or you can think about it as the rank of this matrix -1, same thing. So that's a reminder about what dimension is for a polytope. And so let's think about a very specific example. The Hamiltonian Tor polytope of a complete graph on n vertices. So just imagine building that matrix. There's going to be a column for every variable, and choose 2 columns. There's that column of 1s, we'll come back to that in a second, but there's a variable, for each edge of the complete graph on n vertices, so n choose 2 columns. We're going to have a row for every Hamiltonian Tor. We're going to put the incidence vector of every Hamiltonian Tor as a row. Well, every Tor has n1s in it, n edges for an n vertex graph. So that means that the vector of all 1s is in the column space of this matrix. So if we're interested in the rank of the matrix, we can just forget about the column 1s. That'll be kind of a convenient thing to do. How many rows are there? It's how many Hamiltonian Tors are there? Undirected graph. It's n-1 factorial over 2. Not n factorial, it's n-1 because we don't care what the starting point is. And we don't care which way around we go. So that's why we divide by 2. Every column has n-2 factorial 1s, because think about an edge. I've got to complete it to a Tor. There's n-2 factorial ways to order the remaining vertices. So that's how many 1s are in a column. Well, the rank of the matrix is the same as the rank of the smaller matrix. It's just A transpose A, just simple linear algebra. And what's interesting is this matrix, we'll call it B, doesn't have too many different non-zeros, distinct entries. So, what is an entry in B? It's the dot product of 2 columns of A. That's just counting how many Tors contain a pair of edges, right? Because the 1s in a column tell you which Tors contain an edge, so the dot product will tell you how many Tors are containing both edges. Well, there aren't too many possibilities. It's a complete graph. So either those 2 edges are identical, or they share a vertex, or the disjoint. And then the number of Tors that contain those things are the same. And so you can do these simple kind of counting arguments. Maybe that last one is a little tricky. You have 2 disjoint edges. You take the remaining n-4 vertices and you order them somehow. Now you're going to split it into 2 pieces. There's n-3 places to split it. You're going to take one piece and hook it to the top of these 2 edges, and the other hook it to the bottom. But you could flip one of those, and that's why you get the extra 2. Because of that there are only 3 distinct entries, you can view B, A transpose A, as a weighted sum of 3 matrices. The weights are just these numbers, and the BIs are the incidence relations of these edges. So B0 is just the identity matrix. It's just capturing when did 2 edges, when are they identical? This B1 is the incidence matrix of the line graph of the complete graph. It's just asking when do a pair of edges share a vertex. If you think of a new graph, a line graph, we have a vertex for every edge, and then you make things adjacent if the edges were adjacent. That's the line graph. This last one, B2, would be the complement of the line graph. These three BIs without the tau would add up to the all ones matrix because they're partitioning the all the pairs edges. So that's the matrix we have, and we want to know its rank. Well, these are really nice matrices. I don't know if you know what an association scheme is. I didn't know, but I didn't know any of this. Really any of this. But these matrices are symmetric matrices that commute. For symmetric matrices that commute, they form what's called a linear associative algebra. So if you look at linear combinations of these matrices with complex coefficients, that's a vector space. There's a multiplication rule for that vector space. That's an algebra. And these matrices not only do they have that property, but because of that, they simultaneously diagonalize. So that means that the eigenspaces of each of these are nested in a super nice way. Yeah, so I didn't know any of this at the time. I'll come back to where, how I learned about all of this, but this is the multiplication rule. So if I have two of these matrices and I want to know how they multiply to get, again, a linear combination of them, that's what proves it's an algebra. There are these numbers here. These are called structure constants. They have a very nice combinatorial meaning. So I wrote it here for more than those three classes, 0, 1, and 2. You could have more classes. What these numbers count is I take two elements, here they're edges of the graph, that are related in the ith way. The ways we have were 0, 1, and 2, how many vertices the two edges share. So I take two edges that are related in the ith way and I count how many edges are related in the jth way to the first element and the kth way to the second. That number of those is Pijk. So in other words, everything in this picture is fixed, and you're just saying how many G's fit this. And those are the Pijks, and you pop them into a matrix in this kind of recipe. And well, here they are for this kind of association scheme, these three matrices. Who cares? Well, this matrix, 3 by 3 matrices with the same weights as before, has the same minimal polynomial as this matrix. This was a lot bigger. This was n choose 2 by n choose 2. They have the same minimal polynomial. That means the non-zero eigenvalues are the same. So the minimal polynomial, this is the lowest degree monic polynomial that I teach. So I can just pick, yeah. That's where these matrices, where you get the zero matrix if you plug in this matrix for lowest degree monic polynomial. Anyway, the point is that one way or another, these matrices have the same distinct eigenvalues. And so what you can do is calculate symbolically the eigenvalues of these 3 by 3 matrices, right? This B matrix that I defined here is just a 3 by 3 matrix. These taus are things like n factorial. These numbers in here, well, I don't know, but I go to this thing, and the taus are things like n factorial, and these things you saw, they're like n minus 4, things like that. So you have a 3 by 3 matrix of symbols in n, and you can go and write down the characteristic polynomial. It's just a 3 by 3 matrix, and you can automatically, with some computer algebra software, calculate the roots. So you can get the distinct eigenvalues of this, but they are the same as the distinct eigenvalues of this. Now you just need to know what are the multiplicities of those eigenvalues back over here. So this you do symbolically at another level. You say that the trace of this matrix, B to the L, is just this weighted sum of the eigenvalues raised to the same powers. So if it was just trace, L equals 1, it's just the sum of the eigenvalues, but weighted by the multiplicities. But it works for B squared. You just use the squared eigenvalues, etc. So I can write these equations down for L equal 1, 2, and 3 and get 3 equations in 3 unknowns, the multiplicities. And I can go and solve that and get the multiplicities. Why do I want the multiplicities? Well, now I know the eigenvalues. One of them might be 0, but The other ones probably won't be. And then I can just count now how many non-zero eigenvalues are there in B. That's the rank of the matrix, and I'm done. So it's kind of a program. It works not just for complete graphs, it works for other nice structures, complete uniform hypergraphs, complete directed graphs, bipartite graphs, works for messier things related to subtour elimination faces of the Hamiltonian Tor polytope. Anyway, yeah, so, you know, I did this, I played with this. If you want to look at this Hamiltonian Tor polytope, you actually need to work with 20 different relations. That's much more complicated. It's not symmetric anymore. And so these things don't simultaneously diagonalize. So I had to learn about things called coherent configurations and completely reduced forms of algebras. And she's having a good time with this. And no, really, it was like I learned so much, and it was just so exciting to, you know, that child that I showed you back there. Yeah, so, you know, how did I get into this at all? Was that at the time, polyhedral combinatorics was a big deal. And this was what I mean by that. There's lots of that could mean different things to different people. What it meant, you know, from the OR perspective was looking at NP-hard combinatorial optimization problems like max cut, linear ordering problems, and trying to get partial characterizations of the convex hull. Try to find some of the facets, characterize them, find separation routines for them. And then for very special cases, planar graphs, things like that, you would try to get a complete characterization. So this was a super popular thing back then. I was working on unpopular things like oriented matroids. So I don't know, for one reason or another, I decided, you know, to start doing this. I don't think it was because it was popular, but just somehow. So I was looking at some polytope. I'm not even sure. I think it was a variation on what's called the equally cut polytope of a graph. And I wanted to start doing some of these kind of investigations. So, you know, what I did was I computed. Not computed how I just described, but you remember the definition of the dimension. I wrote out for my polytope of interest, like I picked n equal 14. And I had a polytope with, you know, lots of extreme points, and I wrote out all the extreme points. You know, I wrote some little 3-line code to do that, compiled the code probably by Fortran. And then, you know, I had this matrix, you know, maybe it was, I don't know, 300 rows and 17 columns. And I used some software, ISPAC is something that's part of LAPAC now. And looked at the singular values of that matrix, because I learned in graduate school that if you want a good handle on what's the rank of a matrix, you compute the SVD and you just count how many non-zero singular values there are. And if you look at the smallest, you know, non-trivial one, it'll be, you know, who knows what, 10 to the minus 3. But then you're going to see one that's like 10 to the minus 15, and that's 0. And so this was just to get a little computational evidence to try to see if I could guess a formula for the dimension of this polytope, and then I was going to go ahead and try to prove it. But I always like to do that if I can get some computational evidence. But I saw the weirdest thing. So I did what I said, and there was one big non-zero singular value, some strange number with decimal places, and then all the other non-zero ones were the same, and then some zeros. It's really strange. I had done this before for other matrices, but I knew this was kind of a combinatorial matrix. It was a 0-1 matrix, but there's no reason to think, you know, a general 0-1 matrix would have so few distinct singular values. So I had this thing. It was like about this big. It was called a calculator, and it had this funny key on it. The key was it looked like this, key, and it had like that on it. So I pressed that key with one of the numbers of these singular values in there, and it was an integer. So the numbers were square roots of integers. So, you know, I was, you know, smart enough to think if it's a positive integer, it's counting something. What is it counting? I had no freaking idea what it could be counting. So I went to the library, like the buildings, you know, with books. And at Yale, you go on a tour. So there was the engineering library, the math library, and Cole's Foundation, where Herb Scarf and Martin Shubik Martin Schubig's one of the people that interviewed me when I got a job at Yale. She was mentioning Schubig before. Anyway, so I do the tour, and the last stop on the tour, in that there weren't so many tours of 3 points, but the last time I stopped at the math department, and I'm looking across the books, and what am I looking for? I'm looking for inequalities about eigenvalues, because I think I'm going to get lower bounds on these eigenvalues, and if I get good enough lower bounds, I'll be able to show that the rank is at least something. Usually for these things, you know the rank is less than or equal to something because you know some equations. So you want to show the rank's at least something. So I'm looking and looking and looking, and I stumble on this book, Spectra of Graphs. I saw it there. I wasn't, I was looking at inequalities about eigenvalues, and there was Spectra of Graphs, and I knew that was it. That was my destiny. I knew it. I don't know why. I mean, I just knew that these eigenvalues and graphs, well, my problem had to do with graphs, but I knew that's what I needed. So I opened it up right there. I didn't even like run back to my office with it after checking it out. I opened it up, and inside was a golden ticket. Yes, it was all this stuff about association schemes. And then, all of a sudden, because I hadn't been thinking about A transpose A, I was really thinking about the singular values of A. And so all of a sudden I started thinking like eigenvalues, singular values. I remembered, yeah, there's a very clear relationship. And so that's when I started to learn about all of this. And I pushed it so far, and that's when I gave that talk at Cornell, and they said, no, you really have to go talk to Alan Hoffman, who knows. So Alan showed me a lot more about the spectra of graphs, where I could, fill up 4 papers. So Alan pointed me to this book, and I found these other papers by Higman, and had a lot of fun. By the way, at the time I was using this symbolic software called Maxima, which was something that came out of MIT well before Mathematica and things like this. It was quite funky. It knew like that n squared divided by n was n. And you could work with factorials, but it didn't know like n factorial divided by n minus 1 factorial was n. Didn't know that. Well, sometimes it would, but if there was like a 7 in front of it, then it wouldn't. So you had to, what I'm saying, you had to coax it a lot. And that was an interesting experience, sort of using this symbolic software, but having to help it along at various places because it got confused because of all the factorials. Anyway, this is Alan Hoffman. Not when I visited him, I showed you a picture, but he was young once as well. This is a pivot, by the way, in the talk. So Alan was young too, and I'm going to tell you a little bit about one of the first problems he looked at. Well, he was a postdoc of George Danzig's. Danzig was young too. There's a pattern here, actually. So that's not the normal picture you see of Danzig, but that's how he looked back even before Alan was his postdoc. So so Alan was his postdoc, and the first problem he gave Alan was he told him, I have this way to stop the simplex method from cycling. He didn't say cycling, by the way, he said circling. We'll come back to that. And but I don't know if it's really needed. I don't know an example where the simplex method could actually circle. And so can you go away and be a postdoc and come back and figure out whether there really are examples like this, or whether there aren't, and maybe we don't even need this proof, that maybe the simplex algorithm can't circle in any case, even if there are degeneracies. So Alan went away for 2.5-3 weeks, and he came back with an example with 3 rows, 10 columns, and I didn't have a postdoc. I mean, some of you had postdocs. Week 3, I mean, Danzig gives you a problem, he doesn't know how, and like, you come back with the answer. He must have felt so good. Here's the example. So it's in, it's hard to see, but even if you're up close, it's hard to fathom. This is in Danzig's book, Linear Programming and Extensions. It's not called linear programming, et cetera, et cetera, et cetera. It's linear programming and extensions. But that's what it means, linear programming, et cetera, et cetera, et cetera. So this is the example. Now, there's some strange things about it. There's this first variable here. It only occurred, this is a tableau, by the way. I don't know if you're familiar with those things. The top row, there's a right-hand side of one, and there's nothing else in that top row. So this variable doesn't move anywhere. Why is it even in the example? I think it's only there. I don't have a conclusive proof that he wants a non-degenerate example. So he put that there, and now it's non-degenerate. It's not fully degenerate. But the rest of it, like there's this theta is 2 pi over 5. Then there's omega should be bigger than 1 minus cosine theta divided by 1 minus 2 cosine theta. And then you see the iterations. It says cycle 0, cycle 1, cycle 2. It's one circle, but he called iterations cycles. So that's why he called cycles circles. So look at the entries. They're wild. Cosine theta, sine theta, tan theta over omega. What the heck is going on? You can notice, like this row, the omegas are in some of the denominators, but not all of them. Then up here, you start to see an omega up there and down in the objective row. What the heck is going on? So I sought to figure out what was going on. And so that's what I want to talk about a little bit. But Hoffman never published this like as a paper, but he had a National Bureau of Science technical report, which I got a hold of, which is another story. But he wrote, finally, we regret that we are unable at this stage to recall any of the details of the considerations that led to the construction of the example beyond the fact that the geometric meaning of the pivot rules of the simplex method was very much in the foreground, the geometric meaning. Now, we all know the geometric meaning. We've been talking about it for, our adult lives, right? And Beal said something similar, like not easy to grasp what's going on. So at the time, that's me. The glasses are getting still bigger at this stage. So that was my mugshot at the University of Kentucky math department that I joined around that time. And it was a math department. So I left business school. I was in a math department. Life is nice in a math department. You sort of do what you want and look at examples of cycling. You can't do that in business school. They'll kick you out. They will kick your ass out. So I wrote an email to Alan Hoffman, who I had met, over the whole spectrum of graphs ordeal. So here's the email, August 3rd, 1994. When did you start your PhD at Kentucky?
1990,
right around that time. So she's coming in the door like, get out of here. I'm busy sending emails to Alan Hoffman. Hi, Alan. Something has been bothering me for a while. So I thought that I would resolve it by going to the source. In Danzig's linear programming book, he refers to the repetition of a basis by the simplex method as a circle rather than a more common cycle. He prefers to refer to that. Anyway, the term circle seems rather appropriate when he gives your example with the entries in the simplex table. I don't like Tableau. Are ordinary trigonometric functions, exclamation. And now my question, how did you concoct this example? It was only 43 years ago. Surely you remember. Now, I didn't know Alan that well then, but I've talked to people subsequently who knew much better. And yeah, his half-life was well below 43 years of remembering something. A few weeks even. So this is what he said, or let's say at least 2 months. So he took 5 days to respond. So, it's faster than the Pony Express. And 2 months after I made up the example, I lost the mental picture which produced it. I really regret this because a lot of people have asked me your question. I can't answer. Best regards to Carl Allen. Carl Lee, who also was a graduate of Cornell and did polytopes and knows what a circuit is. So, what would you do at that point?
Try to redraw it.
These new graduate student. Yes. No, I couldn't blame. I'd given it to her, but she, this was like she just arrived. She wasn't my student yet, so otherwise you would have received this. So I spent the summer like trying to figure out, not that summer because the summer is almost over, but I had to get that Bureau of Standards technical report, which took months and months. It's a long story. So I had to go and do my research about, look at Alan's paper, his technical report. Maybe he'll explain. He didn't remember, but maybe he would have revealed in the paper what was going on in his mind. So I tracked down the technical report, and it was clear what his mental picture had to have been. And it's something called the column geometry of the simplex algorithm, which most people don't know about these days. So it's not the vertex, bouncing around the vertex picture at all. It's not the picture that Hoffman had in his mind, surely, because he was Danzig's postdoc. When Alan went to Danzig, he didn't know anything about optimization. That's the other thing I should have said. So Alan gave him this problem, explained the simplex algorithm, and said, and now, figure out this this thing. But he didn't even know the simplex algorithm, and he still, in 2.5 weeks, came up with this example. But what's clear is that that wasn't how Danzig was thinking about the simplex method either at that point, around the extreme points. So what I did, I spent the summer on this because I get obsessed about things. And I worked out the algebra in a much cleaner way to try to understand what those examples look like. And you can make these examples for, instead of 10 pivots, there were 10 variables there. You can make 2K pivots and make a family of examples that cycle with 2K pivots. For any K at least 5, you can't do it with K equal 4. That's why his example is a minimal of this type. Yeah, Alan, I got him to confess. I have a video of it. So he confessed that I did figure out what was in his mind. I think John wrote an article about it. I think succeeding in what my mental processes were at the time. But I think John succeeded. That's the best you're gonna get. So anyway, let me switch out to some Python. And where is it? Yeah, so here's the example. Now, the example, there's no omega. The only reason the omega is there is so this Mathematica figured this out for me. So at the time I was using Mathematica, and I made a plot of Alan's example using Mathematica, but in this so-called column geometry. I'll explain what that is, and maybe I should go back to that actually. Yeah, let me explain the column geometry before I show you the, yes, let's do that. So yeah, I made this plot, and Mathematica scaled it automatically to make it nice for the user. And basically what it did was it scaled the omega out of the problem. And then when it looked so nice, I stared at that problem more, and I realized the only reason the omega was there was to make Danzig's rule cycle. So Danzig's rule is pick the biggest reduced cost if you're maximizing. And Alan came up with this example, and then either he went back to, that's what I imagine, went back to Danzig, or on his own said, well, let's get Danzig's rule to cycle, because otherwise, he's going to go there. Here's a cycling example, and Danzig will say, come on, yeah, sure, but get my rule to cycle. So you can scale that omega out, and now you're not following Danzig's rule, and the omega really shouldn't be there. It was just a hack at the end to make Danzig's rule cycle, and Mathematica figured that out. Here, let's go back here a second. Oh, that's a picture that I'll show you in a second. That's my picture on this collected papers of Alan Hoffman. That's my only published artwork. Well, I do have published poetry. Yeah, let me explain these column geometry. Yeah, the column geometry of the simplex algorithm. So this is what it is. This is the way they were thinking back then. You have a standard form problem, and we're minimizing. And you build these columns that are of length m+1. M is the number of rows of A, but you put the objective as an extra entry. So these vectors live in R m+1. And you put this other thing called a requirement line. That's what Danzig called it. It's the B vector, and then a Z there, which is another variable to capture the objective value. And then you think of the problem, the linear programming problem, this way. Go away. Yeah, it's you think about this cone here, and what you're trying to do is write the vector ZB. Z is a variable, but you try and write the ZB as a non-negative combination of the columns of the matrix of CAs. And so that's what this is. These are non-negative combinations. And so it's a cone. And this cone is somewhere pierced by this line. And those values of Z that are obtainable are all the possible objective values that the problem can take on. And what you're trying to do is find the lowest point on that line because you're trying to minimize the objective. So just to give you a little picture of a kind of pivot.
Click more and then click hide.
Click more and then hide.
Or,
No,
oh, sorry, yeah.
hide what? Loading, that one,
Yeah.
right there?
What?
The one above it? Escape to show, no, see, you think escape is gonna make that go away. Go be patient, I'm patient. Yeah, so this is interesting, what Danzig wrote some years later in his reminiscences. The particular geometry used in my thesis was the dimension of the columns instead of the rows. This column geometry gave me the insight that made me believe the simplex method would be very efficient for solving linear programs. By great luck at work, blah, blah, blah. So here's a pivot. So this is the cone I talked about. So that's all non-negative combinations of these vectors. Down here would be where the columns of the A matrix live, but each point is just lifted up by its objective value. And so a basis in this picture would be two of these generators. Just think Alan's example had 2 rows, really forget about that silly extra row. And so that two-dimensional yellow simplicial cone is pierced by this so-called requirement line. That's the objective value of the solution. And so what is a pivot now? I think about something else lower down, like this point that's below the plane, spanned by the this yellow this yellow simplicial cone. And so I think about that plane, and this point here is below it. And so I build now a m+1 dimensional thing, or sorry, an m dimensional thing. And that's this bigger simplex. And well, this line pierces some other facet of that simplicial cone. It pierces the green one. And so there's only one point in this simplex that is not on that facet, and it's this generator up here. So you get rid of that generator and you add this generator. Now you're at this green simplicial cone. And that's what the simplex method does. It just wiggles down, dropping one, adding one, and gravity takes it to the optimal solution. Gravity. I mean, you can't go wrong with gravity, right? So that's why he thought the method would work well. It's just right, like snowflakes, and you know, like going around the boundary of. I mean, he never would have thought this would have worked. So yeah, that was his picture, and that's what made me think about plotting this in the column geometry, and that's where I started to see what was going on. By the way, it's really hard to draw cones; they go on forever. So these are actual simplices. Okay, now why simplices, besides the fact that I can't, you know, draw forever? At the time, von Neumann and Morgenstern were publishing a huge book about game theory. And in game theory, the variables are probabilities of playing strategies. And there's a famous meeting that took place between von Neumann and Danzig. And so he had all this on his mind. And you can now view it for a game theory problem. The simplex method is actually using simplexes. And so instead of these cones, they're actual simplices working their way down. That's why it's called the simplex method. Teach people that. Otherwise, isn't it strange? You teach linear programming, you say there's the simplex method. Nobody says why. Thank goodness, because you didn't know. Okay. So yeah, now let's go back to. Yeah, so I wrote this, this is Python, but at the time I wrote this in Mathematica, but let me just show you this picture a little better now. Where is it? Here. Oh, there was the more, and then the high, see, I can learn. Yeah, so this is Alan's, oh, nope, wrong one. Sorry, this is Alan's example. Let's look at it from above and forget about objective value. Oh, maybe I have to run it again. It went to sleep. Let's try that. Yeah, so that's his example, but let's get rid of the objective value and just look at it from above. Something like that. What you see is these 5 inner points. It's not really perfectly straight, sorry. Yeah, that's better. You see these 5 inner points, and you see the 5 outer points. The 5 inner points equally spaced, 2 pi over 5. That's where that theta equals 2 pi over 5 is coming from. But these outer ones are equally spaced. And if you take the inner ones and you rotate by exactly 90 degrees, you get the 5 outer ones. But actually, all of these points in 3 dimensions lie on a common plane. So if we go back here, and we tilt this the right way, so really what's going on is there's 2 concentric cylinders and a hyperplane that's cutting those 2 cylinders. And you pick 5 points on the inner one and 5 points on the outer one, but the 5 on the outer have to be shifted 90 degrees. This is what Alan was thinking about. And if you try to do this kind of origami with 4 points instead of 5, you can't make it work. You just can't make it cycle. It just won't do it. You really need this kind of 10-pointed origami. If you're more of this kind of person, so this is the same problem, but now I did what Danzig prescribed to do, the epsilon perturbation. So if you pick a basis, a feasible basis, there's lots of them. It's fully degenerate, so all the bases are feasible. You try and discover, is the problem unbounded or is the origin optimal? That's what you're trying to do for a fully degenerate problem. So you perturb the right-hand side by epsilon and epsilon squared. You find this first variable, variable number 0 wants to enter the basis. It's got a negative reduced cost. And if you just follow this perturbation in 2 pivots, here, I won't drag you through all this nightmare, but here's like the next pivot. This thing is feasible in the epsilon world. It's got this negative coefficient on epsilon squared, but it's got a positive on epsilon. So for small enough epsilon, that's positive. This one is pure epsilon squared. And that's a feasible basis. It's really 0 in the original space. And, it's really 2 pivots, and then boom, all the reduced costs are non-negative. So everything is right with the world. Yeah, so let's go back. I have 3 hours, you said, right?
Yeah,
What time is it?
it's 11:20.
Oh, it's perfect.
2 hours.
Perfect. Yeah, anyway. Yeah, so I was thinking more about computing and being young and the first things you work on. And computing, years ago wasn't the same as it is now. So the first linear program was solved by hand, and it was not a trivial problem. There's something called the diet problem. You've heard about this before. But there's a paper in the something like the Journal of Farm Economics. And the person there had all his data and a problem with a reasonable number of constraints. So you couldn't draw it geometrically. It wasn't like making, 3 kinds of sausage from 2 kinds of meat. And somebody got offended by this sausage. But anyway, he got the data, and the person who wrote this article in this Journal of Farm Economics, Stigler, I think, they had a heuristic solution for this LP, and it actually wasn't the optimal solution, and it was only by doing computing that it was determined that wasn't the optimal solution. So nobody had computers at this point. So there was something called the Mathematical Tables Project of the National Bureau of Standards. And it was a bunch of people in an office building in New York City computing with desk calculators. And there was this guy, Jack Laderman, who Danzig knew. And you can find many quotes. This is a quote in a tech report of Danzig's. There was about 25 people got busy working on this solving by the simplex algorithm. They each had a piece of the tableau, and somebody would probably call out through a megaphone, subtract 1/3 of row 3 from row 6. I imagine that's how it must have gone. And they did it somehow. I don't think it was 25. If you look at other quotes about this, sometimes you see numbers as small as 9 or 12. 25 seems like, like in history, if the fish gets bigger and bigger that you caught, I think it's a bit like that. But anyway, you can hear him talk about this incidentally on, there's a video of this on Inform's website. You can hear him talk about this exact problem. But they did this, with a team of people, and that was the first solution of an LP by the simplex method by hand, just like you probably did when you were a student. I did. This is a little side note. My first graduate student was Judy Bender. She was a single mom, and we wrote a letter. People wrote letters back then, especially to older distinguished people. So we wrote a letter to Danzig to tell him what we were working on, and because we had noticed it related to something in his amazing book. And this was a quote from her, the acknowledgments in her thesis that Danzig sent encouraging, inspiring words that thrilled her. It reminded me of that I talked to Hoffman, and he sent me in person very encouraging and important words at a time where when you're working on your PhD, you have a lot of uncertainty where how things are going to go, and a little bit of encouragement from a lot of people like you to some of the other people like you is a nice thing. So if you want to hear Danzig talk about this, there's a link there. This is one more interesting point that I'd like to make. Back then, this 1960, that's the year I was born, there was this paper in Econometrica on branch and bound. This is the first paper on branch and bound. These two people invented branch and bound. And now try to publish a paper on branch and bound in the journal Econometrica, I doubt it. But at the time, Land was at the London School of Economics, where our friend Latsi is. And you're in the London School of Economics, essentially a business school. You probably publish in Econometrica. You're not going to publish in Math Programming or Journal of Optimization Theory and Applications or Math of R, because those didn't exist for about 15 more years. So that's where it was published. I purposely didn't put their first names. They omitted those when they submitted it. So they really thought it would be badly received. And it's heartbreaking. Anyway. That's the sign that was knocked down.
Thank you, Tom. Let's open for questions on Zoom first, please.
Sure. Do I have to do something to? No.
No, the audience has to do something.
Stephen.
Oh,
I was just saying a very nice and interesting talk. Thank you very much.
You're welcome.
All right, let's move to questions in the room, please.
You.
did you know Danzig in person?
I never personally discussed them. So I was at lectures he gave,
Mhm.
but I was a grad student at the time. I wasn't gonna, say anything to Danzig. But Kurt, my friend, he was Danzig's student, so he told me about meeting Danzig every week, and said he was a very, sweet guy.
How many female PhD students have you had? Or like, what's the ratio? Because I feel like three.
Well, those
are-
two, Judy. I never really thought about their genders. Let's see. Well, right now is Hessa, and let's see, that's a male. That one's a male. It's about half, I think. Yeah,
That's impressive.
something like that. I think in our department, maybe half of the graduate students in general are women.
No, in the area.
Oh, Joy and Kentucky, Joy. That's right.
More questions? All right.
Well,
Let's-
no,
Go ahead.
not fast enough.
Can you share the 3D picture again and of can you just say where the
Yeah, maybe I didn't quite say as much.
the
Yeah, sure.
Kelly cycle happens?
Well, it's a bit hard to see because it's fully degenerate. So,
So there's one objective line going down?
yeah, so the objective line is right through the center of this. And you're just re-expressing the origin with these planes. So to really check this, you have to look at this and see, you know, which things are sitting on the correct side to see that it's a valid pivot sequence. I had a physical model of this that I had made in Kentucky. So, you know, I didn't have all this fancy way to, you know, this is a little dissatisfying two-dimensional projection of this. So I got a ball. I couldn't afford a ball. So, but there was a machine shop where like experimental physicists work, and they took a cylinder of some kind of lightweight metal, and they milled it down so it was almost a ball. It was cheaper than buying a ball, and they drilled holes in this at the, you know, right angles that I prescribed for them. There was no 3D printing or anything, and I, you know, bought little metal things and I put them in, and I could really kind of. You probably saw it in my office, and I probably tried to explain to you, and you probably just ran out of there in fear. But yeah, the 3D model is better to actually see that these pivots are really valid, because things have to be sitting on the right side of things to make it a valid pivot. You won't move from the origin, but to see there's a valid pivot sequence, you need to make sure the origami is correct. Anyway, there's an open problem session, which also has to do about degeneracy on Thursday or something like that. Thursday. So that's part of the reason why Drew insisted that I give this talk, was to make kind of have an entry into that.
Yeah.
She said.
All right. Okay, so let's thank John again. Our first speaker is going to be Daphne Skipper. We're very much looking forward to your talk. Please go ahead.
All right, thank you. So this is very, very big, diverse, you know, way far away from what we've been doing the last day. My motivation for this is really because this is what I've been thinking about this year, because I have this student, Gunny. I work at the Naval Academy, and I don't have grad students, I have undergraduates, and they do senior theses. And this was his senior thesis. And when we were working, trying to figure out a problem to do, and I chatted with John, and he said that Luz has been wanting to work on this gas network problem. And I thought, oh, this seems like a good thing for an undergraduate to work on. And boy, it got very involved. And in a way, I feel like for me, it was a very good project, because a lot of the work I have done has been looking at nonlinear structures, very sort of basic nonlinear structures, and seeing good modeling strategies for them. And I've been looking at these from a pretty theoretical point of view. You've probably seen some of John's talks on volumes and Luz. So looking at nonlinear optimization, really mixed integer nonlinear optimization from that perspective. And I had never actually myself tried to solve like a hard, application problem that involved, integers and nonlinearities. And so we just kind of dived in and worked on it. Probably something that you don't realize, a lot of you have been talking about the simplex algorithm, and that's actually used to solve optimization problems. And so I'm teasing, I know you know that, but this is somehow a little bit related to some of the things we've been talking about, if tenuously. So this is Gunny Kim, the student that I worked with actually, I didn't mention my colleague, Chris Lorenzo. We kind of tag team with him. Chris is very much more of a computer science kind of guy. And so he was very.
Just share your screen on Zoom. They can't see it through the camera.
Oh, sorry.
No worries. I just
Okay.
stuff in my hair.
Okay. sure, let me make sure I'm seeing the right thing here. Yeah. I think this is what I want to share. And then. Okay, is that good? Can you see it good? Okay, good. All right, so anyway, this is Gunny, and poor guy, he suffered through, I mean, no, he really loved this gas network optimization problem. He sent me this picture so that you could, have a view of him. He probably wants you to think he's a hockey player. That's the kind of guy that he is, but he was just there at the hockey game. Okay, so getting into this problem a little bit. So when I say gas network optimization, what I mean is natural gas transport. So transport of natural gas, and these kinds of networks, like all networks, have long haul line. Well, these kind of applied networks, not the kind of networks that you work on, have maybe long haul pieces, and then they have local pieces. And what we're really focusing on here is long haul pieces. And in the Americas, the gas networks are really owned by private companies, and they completely control all aspects of the network without a lot of interaction between them. And so for these kinds of networks, the goal is to minimize cost, generally. However, in Europe, the different companies have to work together more. This is just stuff I've read. I know I have like this much knowledge about this really, but I'll tell you a little bit of the motivation here. That the companies have to work together more, and they have to meet these government regulated quality standards, which means that they have to supply gas at the output nodes at a certain level of heat power, really, which has to do with properties of the gas that gets to each node. And so for that reason, there's this reason that they are interested in a so-called mixing problem, which is what I'll be talking about a lot. And the optimization goal is this nomination validation, which basically means, is this a feasible flow through the network that meets these government standards? So gas networks, it turns out, are super complicated and involves modeling fluid dynamics, thermodynamics, chemical engineering. And in this case, with this problem I'm talking about, it requires mixing of gases, because we're taking gases with different properties from different sources, and then having to meet demands of gas with certain properties at the different exit nodes. So in this model, and we are really drawing from a paper, this paper that Luz shared, hi Luz, they kind of simplified things by really focusing in on network flow, which is something that I'm sure everybody here is very familiar with, and then gas pressure, which turned out to be pretty interesting, and then gas quality. So this gas pressure is a nonlinear pressure loss model that you'll see. And then gas quality is also a nonlinear mixing model. So these are the things that introduce the sort of complications to the problem. There were some simplifying assumptions that we made also that were in the paper that we were basing our work off of. Constant temperature throughout and zero slope in pipes. Okay, so here's a picture of the simplest gas network that we actually did our computations on. This is GasLib is a library of gas network instances that was developed by a group in Germany. Actually, here are their names down here. And to allow people to practice, have a test base for working with these optimization models. And you can see here that we've got entry nodes, or here's the little key here. There are entry nodes and exit nodes, and of course, internal nodes. And we model all of those. And then the rest of these are all basically the arcs in the network. So there are compressors, and compressors increase the pressure in the system. And so pressure is is part of the model that we're looking at. So as the gas goes across pipes, then there's this pressure loss that occurs that you have to model. And so the compressors are a way to increase the pressure because the pressure has to be between certain bounds. So compressors increase pressure, control valves release pressure, and then resistors and valves are two network elements that we are not messing with. They are another very complicated nonlinear model. And then pipes are just simply like really what you think of as the arc in the network. And this is where the pressure loss occurs. Okay, so so going back to here, I will show you the model for network flow, which is pretty straightforward, and then quickly show you a model for gas pressure. And then we'll come back to that at the end. But the bulk of what I'll be showing you is models, a lot of different models for this mixing. And the mixing is the thing that's the newest thing that people are working with in this area, to be able to get a mixing model that is manageable enough computationally to be able to put into these much more complicated nonlinear models and to be able to actually, get somewhere with them. Okay, so here is the model for flow balance and pressure, not including pressure loss, because that's going to come later in this nonlinear formulation. So what I've done on most of the slides, at some point I kind of got lazy, but for most of the slides, the red indicates it's a variable, because as you know, when you're looking at these kinds of models, looking at the variables is how you know what kind of nonlinearities you're dealing with. So I'm going to just put a little bit of notation over here, because, if you're trying to actually follow along with how the model works, it's helpful to understand and to remember what all the notation is. So we've got delta A. So whenever there's an A, that means that we're talking about an arc variable. And then if you see a U or a V subscript, that means it's a node variable. So delta A, this is the change in pressure. So this is greater than or equal to 0. So it's an absolute value change in pressure. And so what we're trying to do in this model is minimize the change in pressure at the compressors. So the compressors are the ones that are increasing pressure, right? So this is an expensive thing to increase pressure versus a control valve. I have no idea, but I imagine, there's some kind of like thing that you open up and release the pressure, right? Versus some tank or, some sort of engine that has, I don't know, motor involved to increase pressure. So in this model, the goal is to minimize this effort, this work to increase the pressure as you go through the network. And then this should look quite familiar. Once you know that Q represents flow. So this is just a flow balance constraints, and this is happening at all the nodes. So QA, this can be negative or positive, because negative represents flow backwards through a directed arc, and positive is in the forward directions of the arc. So this is flow. And QU nom, it kind of looks like a variable, but this is, whenever you see the nom, that means that this is the flow into the network or out of the network, right? So it's going to be 0 at internal nodes, it's going to be positive at a source node and negative at a sink node. And then we have these two right here, just modeling the thing we're trying to minimize. And actually, I don't even know that we need this when I've looked at it again. But so if you have an arc UV, going from U to V is the forward direction of the arc. And so if you have an arc UV, then you would expect the pressure to be less at this is actually kind of looking backwards to me, but I think it's probably right. But so pressure is going down from U to V as long as it, oh no, this is a compression. This is a compressor. It's a compressor. So these are only compressors and control valves. So at a compressor, the pressure is going up. So you would have a higher pressure at the end of that arc versus the beginning of the arc, because you're increasing pressure. So when you do PD minus PU, you get a positive, and this is actually what we're minimizing. And then these are just variable bounds. Okay, so that's nice. And notice that all linear, very nice at this point, right? Okay, okay, so we have now the pressure loss model. So this is already not so pretty, right? So the phi here represent, it's an approximation of an even nastier engineering model for the loss that occurs as gas flows through a pipe. And this involves lots of quantities that are, it turns out, not so easy necessarily to find in the data. But there are things such as the length of the pipe, the area of the pipe. I feel like this is diameter, although it's kind of weird to have area and diameter, but I kind of think it is. Or there's some sort of friction constant going on in here. There's temperature, which we are assuming is constant. There's specific gas constants in here. So there's all these things. So this is all parameters, right? So this is just something you compute ahead of time, and then it goes into this expression here. And then you have this stuff here, which I'll get into later, but basically it's a smooth model for a jump discontinuity situation. And then once you have this value for pressure loss, it's not just a linear thing. There are these squares involved, right? So the pressure at the end of the pipe squared is equal to the pressure at the beginning of the pipe squared minus this thing. Okay, so this is, we'll set it aside, put it on the back burner and move on. Okay, so now we get to the mixing model. And if you know about blending models, it's basically a blending model, but it's kind of yuckier because of this setting. So now we've got, did I miss some variables? Did I put them all? Phi, I guess there's phi, I kind of missed there. It's okay, we're not going to see it too much. So here we've got these H's are entering, and notice H occurs both as an arc variable and as a node variable, and this is the calorific value. So this is the value that we're tracking through the network that tells us how powerful the gas is, right? So that's, so we have H, A, and then this calorific value. And also HU is a node variable. So these are the arc variables and the node variables. And then, so if you kind of look at this, this is all of the nodes except for the source nodes. And everywhere except for source nodes, you basically take the flow weighted mean of the calorific values of the incoming gas at the node divided by the total flow of the gas, and that gives you the calorific value of the gas at that node, right? So it's just a flow weighted mean. And then this is basically the exact same thing, except for that we also have gas that's coming into the network, which is a parameter at that node in addition to the other gas. So why is this so yucky? Well, first of all, it's written as a fraction. It doesn't have to be written as a fraction, of course. So you could, of course, multiply this over, and then you would have these bilinear terms with the absolute values in there. But the really kind of nasty thing is that these are variables. The sets that you're adding over are variables because you don't know which way the gas is flowing. So you really don't know on each arc whether the gas is coming in at that arc or flowing out on that arc, even though it's a directed arc, right? So you have to look at the, this is how the variable sets are defined. you have to look at how the direction of the flow to decide if you're coming in or going out. So the flow into node U is you look at all the arcs coming into U with positive flow, along with all the arcs going out of U with negative flow. And then you can do the same thing with the out nodes. Now, so for mixing, you really only need to look at the gas coming in, but you need to propagate this is propagation. You need to propagate from that node onto the next arc. But you only need to propagate if you happen to be flowing out of that arc. Okay, so this is obviously not something we're going to throw into a solver and expect to behave. So what do you do with this? So here is, this is kind of a stepping stone to where we're going. So this is taking that last model and modeling it with maximizations instead of these so-called variable sets. So we'll just kind of ignore, these are basically exactly the same. So we'll just look at this one, the top one. We have here, what we want to capture again is only the incoming flow. And so if we look at all the arcs coming into the node, we only want to take a positive or 0, right? So if the flow is going out, you don't want to take that. So basically we're looking for the positive flow coming in, and here the negative flow going out, right? So that'll give us all positives. And then the propagation, basically what we do is that we only enforce, so this is kind of an if-then constraint. We're only going to enforce that HU equals HA if there's a positive flow. So this turns into another bilinear thing when you have a positive flow there. If you put a 0 there, then you don't have to worry about matching. All right, so again, this having maxes in your formulation, I think there are probably some solvers that will take this, but also not a great idea. So of course, us all being discrete in nature here with our optimization, we would like to be able to do this with binary variables, right? So what you can do, and with this MINLP formulation, is create a binary variable D sub A that indicates the direction of the flow on arc A. And then you can use these binary variables to actually grab out these maxes that you're looking for. In other words, beta is going to be the positive flow on arc A, and gamma is going to be the absolute value of negative flow on arc A. And so then we have that the total flow on arc A is beta minus gamma. And so, I mean, you know, we do this kind of trick all the time, right? When we want to take a variable that can be all real numbers and turn it into positives, right? And then the rest of the constraints here, basically we turn off beta if, let's see, D sub A equals 1 means we're going flow in the positive direction. So this allows, when D is 1, that allows beta to be positive as we want, because D is 1 means flow in the positive direction. And when D is 0, we turn beta off, because we only want one of either beta or gamma to be positive, and the other one has to be 0. And then similarly for gamma, we only allow it to be positive if the flow is going in the reverse direction. And so just kind of to remember here, DA is 0 and 1. And this indicates flow in the positive direction. And beta and is positive flow, are both beta and gamma are greater than or equal to 0. And this is positive flow, or I should say forward flow. That's the right word, forward flow. So forward flow, and gamma is backwards flow. But the positive of backwards flow. And so once we have, so this is a very natural formulation of these things. And once we have this, then we can formulate our mixing constraints without any sort of weirdness. It's nonlinear, but it's no longer kind of weird, right? So we've got just betas here to capture the flow in, and then gamma is the flow in through an out arc, and everything looks a little bit better. Now we still do have, of course, these bilinear terms all over the place. And then we can use big M constraints to model the propagation. All right, so then this is yet another formulation of the mixing constraints. So the paper that we were reading presented this this MINLP model, and then they presented two different versions of a nonlinear model for this mixing. And so they use complementarity constraints, and so you can see how this works basically the same way. So for both of these, gamma goes away, and instead is modeled by beta minus QA, which kind of makes sense. So if you think about if the flow is in the negative direction, beta is 0, and then you get negative of a negative number gives you the positive gamma. And then this constraint, think about this, instead of being less than or equal to 0, think about it being equal 0. And then you'll see how this works. If beta is 0, then either beta or gamma have to be 0, and things work out right. But one thing that I learned through this is that if you put an equal sign here, that's not happy. And so it works better to use inequalities here, which is why this is a less or equal to 0. This is obviously never going to be negative, right? Because both of these are forced to be non-negative. But for the sake of the solvers, you want to put in an inequality versus an equation. Okay, so then this paper presents this other formulation, which is a formulation that works better with respect to the KKT conditions. So you can verify that you're actually at a local minimum with this model versus this model. And so these were the two models that they were really trying to compare in this paper. And so this is obviously a much lighter formulation, but this one has these better conditions for optimizing over. Okay, so now this is the new mixing formulation, and the only change here versus the last one is that instead of having gamma, we now have beta minus Q to replace those gammas. And then, we're no longer trying to be linear here at all, and so we just throw in a similar kind of constraint to before, like if beta A is 0, then I don't have to worry about propagating. But if beta A is positive, then I need to propagate from U onto A. So these are my new propagation constraints. All right, so then by the way, getting to this point of actually trying to implement all this stuff, it was a mess. Because the models weren't really written in the paper in a way that you could actually implement them. They were, oh, you should refer to this paper, and then you should refer to that paper. And oh, by the way, there's a few typos in here. And it was just quite the challenge. And also GasLib, all of the data doesn't come in nice CSV files, which makes me happy. They're all in XML files, and all of the parameters that are required by the model do not exist in the XML files. So there was this whole game of trying to figure out, like, okay, if I want this bound on this variable, how am I going to put together the stuff that I actually have to make something reasonable? And so, I mean, I'm fairly confident that we did something pretty close to what the authors of this paper did. but would I bet my house on it? Probably not. So anyway, yeah, getting to the point of having these running, it was a big day of celebration. Took a lot longer than we thought. And what we really wanted to do was extend this, right, to work. So here's why. Okay, here's why we really wanted to do it. So so Gunny calls these the German doctors. So when the German doctors did the computational tests on these models, what they found is, of course, that the MINLP did not do well at all. And so they set a 1 hour time limit. They saw with Baron, Nitro, and Antigone. And the conclusion was altogether the results for the MINLP formulation are not convincing. It was impossible to solve 135. I kind of skipped this. So there were 24 node, 40 node, 135 node, and 582 node instances to work with. And by the way, they're all slightly different networks, and so it requires work to be able to move up. And so the 582 node network has a lot, like 500 instances, I think, on that network, and that was where really most of the testing was done. And so what they found is that it was impossible to solve the 135 and the 582 node instances to global optimality within the hour time limit. And only 6% of the 582 node instances that they attempted to solve solved to optimality. Or yeah, so local optimality. However, with the NLP, they found that the second formulation, which is the one that does better, and it's a heavier, but better in the context of optimization formulation, was able to solve 66% of the 582 node instances. And so, you know, we want the MINLP or something with discrete variables to do better, right? We want to see if we can do some kind of formulation here to do better maybe than this 66%. This was also given a much lower time, maybe 10 minutes. So, yep.
What does it mean by solved at 66% of it?
Oh, so, okay. So there were, I think they solved 50 of the instances, and 66% of those 50 they were able to solve.
Okay, thank you.
Sorry about that.
No.
2 minutes or so.
Oh my gosh. Okay. I was expecting a 5 minute. Okay. Okay. So we'll speed on through to the end of this. So let's see. My fault. I should have been paying more attention. So I was planning to do, so what we did is that we first decided to try to linearize these bilinear terms. And we just straightforward relaxation, you look at that, and if you are sort of familiar with these things, which Emily, who's not here, is very familiar with, and Drew, lots of people here are very familiar with the McCormick relaxation. So, so what we did is that we applied the McCormick relaxation, which gives you 4 linear inequalities that supply a convex hull of these bilinear terms on a rectangle. And so here is the McCormick formulation, which I will not go through with you because I can't do it in 2 minutes. And this is now the linear version of the mixing model. And so here are, you basically have to treat each one of the bilinear terms independently. Each one of these in each, term of the sum gets its own 4 constraints. And then they are basically bounding these new variables that we're creating, and they're replacing each of these bilinear terms. Okay, so it turns out that just doing that did pretty well. This is the best nonlinear formulation that the original authors, Amti and Schmidt, had made. And this is that formulation with McCormick. And so it did pretty well with Nitro. Nitro's a nonlinear solver. You have to relax everything. So we no longer have our binary variables. Did really crappy on the global solver. Okay, so that was sad. And then we messed around with pressure loss using the variables that we had already defined. And we were able to simplify the pressure loss equation like this, which is much nicer without all the square roots and stuff. It's an approximation though, so it's an approximation of an approximation. So we would like to work on that more, but it turns out that with that change to pressure loss, we actually got within the ballpark of what the original authors had done. And so we do have some hope moving forward. And we have some plans for how to do that. One thing that we really want to do is first convert the bilinear terms using a univariate formulation, and then we can use linear approximations on those. There.
We'll begin with questions on Zoom. Do we have questions on Zoom? All right, no, all okay. Okay, so we move to the room. Questions in the room? Go ahead.
How close is this to like what they actually do?
That's a really good question. I don't know, but the people who Hanti and Schmidt, whose paper we're working on, they've done a ton of work on this, and I think, and they're very involved. So I think that it's not so far afield. The GasLib, the big 582 node network, was designed to be realistic. Nobody wanted to give their proprietary data, but it was actually built using input from European gas companies. So
What different methods did you attempt for the approximation to, you're saying you simplified it and you approximated the approximation, that was one big.
yeah, this one, that's something I really wanted to work on. And so this is kind of related to some work that I've done with Johnny Lou's, like this kind of smoothing. So the actual HPCC here is this is a graph of their actual, the engineering side of things. And one thing that we did, so basically you can see the approximation, and this approximation here is designed to be asymptotically matching the engineering model, and then also to match the derivative at 0. And that's all these parameters, what all these parameters are in here are for. And so one of the things that we tried, if you just look at this, these square roots are actually models for absolute value of Q. And if you simplify this, you kind of see what's going on here is the absolute value of Q times Q. And if you think about absolute value of Q times Q, it's Q squared, except for you turn around the negative side of it. So you have almost like a cubic, right? And so some sort of cubic would be cool. But what we did, actually, it's not quite like this. It's like this. And so one thing we tried is to connect the two sides with a line, because we wanted to get something quick and dirty, right? Something with a line at the right derivative. And then we just let it hit where it hit. And then we used just some of the either or constraint, or we used basically big M constraints to model this piecewise thing coming in here and then going straight across and then going out. And we ran it. We were so excited for a quick thing, and it was infeasible. And I do not know why. But I do have definitely ideas on maybe trying to match a cubic or a fifth degree thing. Or I mean, this is just a smooth thing. We can just piecewise linearize that sucker, and then everything's linear.
Yeah.
And there is actually another paper that did just that with this, that didn't involve mixing.
Thanks.
All right. Okay, so let's thank Daphne again.
All right, so like the last talk, there are no circuits in here, at least not yet. I'm going to start out with a couple of applications, which is how I first looked at Berry centers. This is very far from being comprehensive of the applications. This is something many people are looking at in a variety of fields. And I learn about more every time I go look at the literature. So we'll start with a few of those, and then I'll show you some of the programming formulations that we can use to find these things. All right, so the very first application of Berry centers that I looked with began with this very well-known machine learning data set. So in this data set, a whole bunch of people sat down and wrote their digits 0 through 9, and then it was used to kind of start seeing if various algorithms could detect what number that is. All of us who've ever tried to grade handwritten homework know that sometimes that is challenging. So actually, these are 2 of the first 4, and already you can see they're quite different. This person drew it bigger on top. This one is kind of lopsided, like it's going to fall over. And if you keep looking through the set, it's even worse. There are so many variations of these things. Our approach, the Berry Center approach to looking at these, is to think about it as if every artist who created these nice digits was given a pen with the same 1 unit of ink left, and they had to distribute all of that ink to create their version of this digit. And so we can talk about this in terms of probability. What's the probability the person put a certain amount of their ink on a specific spot in the image? And that turns this into a probability measure. These are particularly nice probability measures because they have the same support. In this context, support is referring to the locations where you can put the mass. And so this is a regular grid, 1 for each pixel, and then we have the mass that goes with that. A Berry center for these digits looks like this, and has many similar properties. So you can see there are specific pixels in the image where mass has been placed. And a Berry center specifically is one where you can take these masses, slide the blocks around, and recreate these original images with as little motion as possible. So you can just kind of take these and reassemble each of the images, add up the cost of how much you had to move, and that should be minimized. Good properties include the fact that 1, it still rather looks like an 8. So there's a lot of interest in using that as like a template for the computer to decide, match new images to this, what's the distance. There's interest in facility location, because there aren't really that many pixels in there that have mass on them at all. There's lots of empty space, and when you're talking about locations, you want to open as few locations as you can. So those are 2 of the big properties that have driven the interest in these Berry centers. But as it turns out, this is by far the easiest case. This is a dimension 2 image. It is on a nice regular grid. You assume each 8 is equally important, and all of these things make that problem much easier to solve. The next application, or an example of an application that is at a more difficult level, is something like this. So I'm currently residing in the southeast part of the United States, and thus you get the wildfire locations for the southeast part of the United States. I do not claim that this is actually where the wildfire concerns are. I know all you Coloradans are far more concerned about this than the Louisianans are, but the ideas remain the same in either place. So we don't know exactly where a wildfire is going to start. So again, there's this probabilistic modeling coming in. There's a lot higher fire risk in certain key places than in others. And a Berry Center is going to supply that information about how do you respond effectively to these throughout the year. So where should you store your equipment? Things of that nature. And you will see that, in fact, Berry Center would have support points in these kind of clustered areas and let us respond. Questions so far? This is still not that difficult because it is still in dimension 2. A lot of the most recent work has started going up in dimension from this. The natural language processing people have very high dimensional problems and are now looking at Berry Centers.
Are these
Yeah.
like campsite? I'm just curious about the line.
I do believe they correspond to certain trails through mountain ranges, yes. And that's mostly where they start. In the southeast. One of the other things I wanted to mention that makes this a little more difficult is not every wildfire is considered equally dangerous. The ones that are close to cities and property that are expensive are generally weighted more heavily than those that are just kind of out in the wilderness, those in not particularly dry areas. So that also makes this just a little bit more complex. How should we weight these things as we're doing our computation? One last picture before we get into math notation. This is what it looks like on a very small scale. We're creating 3 probability measures here. So the ones in color are the inputs to the problems. We're using the circles to denote how much mass there is at each of these points. So all 3 of these measures have 3 support points. 2 of the support points have mass 1/4, and the last one has mass 1/2, so that it adds up to 1 and is a measure of probability. The black here is the Berry Center. So the Berry Center consists of 4 support points, each with mass of 1/4, and that 1/4 mass is carried in whole to each of those 3 measures. So if we were talking about months, in month 1, June, this wildfire fighting equipment would be used to fight that fire. And then in July, it would be used for this one. And in August, this big one would start and it would get help from 2 locations coming in. This property that each Berry Center support point is linked to exactly 1 destination point is a really important property for these things that we use in developing the models. We call it the non-mass splitting property. All right, so time to do some mathematical notation. We're using the capital P for our measures. They are generally allowed to have support in all of R. So later on, we're going to move our so that everything is positive. The lambdas are the relative weights. Like I was mentioning in the original digital setting, we kind of consider every image to be equally important. We don't really consider every wildfire ignition point to be equally important. So we can adjust our relative importance with those weights. And then we measure the distance using the quadratic Wasserstein distance, which sounds more complicated than it is because we're entirely looking at discrete probability measures in our work. And so it becomes the pointwise squared Euclidean distance. So how far is it from your support point in your Berry Center to your destination? Square it, add all of that up for all of those measures, and that's what should be as small as possible. The non-mass splitting property is stated this way. So the mass associated with each of the support points of the Berry center is transported to exactly one of the support points in each input probability measure in an optimal transport plan, which lets us look at the combinations of input support points. So we generally call these combinations in our writing. This is also a version of multi-marginal optimal transport. That group usually calls them couplings. And so in either case, what you're looking at is how do you tie together these different combinations of support points from all your input measures to create your Berry center. I suspect at this point, you've already got an idea why this problem's not as straightforward as it might have seemed. How many of those are there? Oh, I know, I asked you to do math in the middle of a presentation. Well, you multiply the number of support points you have for the first element of your combination, times the number for the second, times the number for the third, all the way through your number of measures. And assuming that your measures are roughly the same size, you have the size of the measure to the nth. And that's what makes locations like wildfires much harder than the digital setting. Every single combination is different. The middle of those combinations is different. And so you genuinely have exponentially many options to choose from for your berries. We can say exactly where the best point is to put the mass for every combination, and that is the weighted mean. So it's pretty straightforward to prove that if you put mass anywhere but the weighted mean of its destinations, it's not optimal. So you can always shift it over, get a slightly lower cost. And so we do have a finite set of possibilities of where to store our equipment. That's promising. And in the grid case, these overlap a lot, and the size of set S, the actual location possibilities, is much smaller than the number of combinations. And this really inspired a lot of work. They looked very closely at these small sets S, and still kept running into computational problems. And in particular, we were trying to design algorithms to find these while maintaining this sparse support. Qualitatively, we want answers that don't have too many locations in them. And thankfully, there always exists this Berry center that has fewer than the total number of support points minus n plus 1. Or if they're all roughly the same size, np minus n plus 1. And finally, we're to the actual linear program model things. So just a little more notation. Each of the support points in our original measure has a corresponding mass that it wants to receive. The cost to get it there can be computed directly from the support point of the Berry center using that weighted mean from the last slide, or just rearranging a little bit, you can look straight at the distances between the points in the combination. So that's what we're doing here. Assign a variable WH to each one of these combinations, and you get the most standard of linear programs. Minimize the total transport costs subject to satisfying the correct mass to each of your initial destination points, and it needs to be negative. And exactly like we were just discussing, the problem is low number of constraints. That's good. Product of the sizes of variables grows exponentially in the number of input measures. And truly, for the last about 10 years, people in a variety of fields have tried to find efficient algorithms to solve this problem that get away from that exponentiality. We tried and we tried and we never beat it, which of course makes you start thinking the problem is it's hard. Finally, that has also been proven. So just last year, this paper was published proving that it is hard to compute these barycenters in growing dimensions specifically. So as we move up from these dimension 2 problems to now the natural language processing setting with much higher dimensionality, that is going to be very hard. We also proved a couple of years ago that maintaining this sparsity specifically is hard. So keeping this low number of locations, that's difficult. But then there was this positive result also in the last couple of years. For a fixed dimension, you can solve the barycenter problem in polynomial time. And this gives me a lot of hope that we can still make progress on this using circuits. So specifically, they're looking at the geometric structure underlying the problem, which sounds kind of familiar to all the things we've been discussing the last 2 weeks. I am very hopeful, in part because A in this matrix, the matrix A in these constraints is extremely structured. It's made up of 0 1s in a very write-downable pattern. In our implementations using this linear program, we do not store A because of that structure. So I'm very hopeful that maybe the circuits associated with those constraints will also give us some geometric knowledge we could use to create another efficient way to solve this. It is weakly polynomial, not strongly polynomial. Okay, so getting back to what I have done with Stefan. He told me because he's out of the room that I could just take all credit for this, but I'm not going. We began looking at that specific linear program through the column generation strategy. So column generation is really well suited to a linear program that has a low number of constraints and a high number of variables. Iteratively, we introduce new variables to this linear program through a pricing problem. So a lot of our recent work has been on the pricing problem because it really has to be efficiently solvable if you're going to solve it over and over in every iteration. And in the most straightforward classic version of column generation, what that means is finding the index where your reduced cost vector versus your cost is maximized. So what will best improve the current solution? We have exponentially many costs. So in the initial outline of what column generation is doing here, we're basically just shifting the exponentiality from the original linear program to the pricing problem search. Now this search is relatively efficient because again, we don't have to store A, so we can form this pretty well and then search, but still, that's where the hardness moved. So running some experiments with column generation, this classic version, we produced these results. So these are the times to solve the original linear programs. These are the number of variables in them. Eventually solving it directly, I did run out of memory on my laptop and started crashing, which does not happen with column generation. That is good. We did find though that doing one column at a time, which is sort of best for keeping a low number of variables in the problem, was slower overall. There are a few instances where it managed to be a little faster, but again, searching an exponential vector each iteration is not very fast. So just kind of heuristically, we were getting the best results at this point, throwing in n columns per search. So we would take the best certain number that we could find, and just we arbitrarily chose to do the same number as the number of measures we had, so that it kind of scaled with the problem. And that really worked fairly well. But still not enough. So most recently, we've kept going with this pricing problem and reformulated it as a mixed integer program. Instead of looking at the vector of costs and searching the elements, we started looking at the sum of all of those, and this is just a number. However, we're going to reformulate AH and CH in terms of a new variable, Z, that lets us combine some terms and really reduce the number of elements we have to look at. Essentially, we're breaking that combination back apart and looking at individual terms and saying we're choosing a particular xik from a support point for our combination if zik equals 1, and we don't choose 0. And we use constraints that these ziks must add up to 1 to enforce that we are choosing 1 per measure, and that creates a combination. We can also reformulate the costs using these z's. Simple expansion of the cost function, and then breaking these xih's from a specific combination apart into support points from our original measure and combining various things. These xi's turn into these xik's, xj is here, and xj. The variable is z in all of these. Everything else is a parameter. Not linear yet. It is quadratic thanks to this bilinear term. And we did briefly run some experiments just with this quadratic model. The mixed integer program I'm about to put up performed very similarly in our experiments. So we really focused our efforts on the MIP. Altogether, we are solving this mixed program. The ziks that I just mentioned, they do stay integer, but now we're able to replace that product with a standard linearization, and it's able to be a continuous variable due to what happens at optimality. So we want to make these 4 indexed variables as big as possible because this is a positive term and we are maximizing. So they end up going all the way to their corresponding integer variables here. And that results in us being able to kind of mix this together. It does not have to be fully integer, only these have to be integer variables. That is assuming that we have shifted the points so that all the components are positive. I mentioned that early on. In general, the support of these discrete measures are allowed to be wherever you want. But since we are also dealing with a finite number of points, you can also just move them so that they are always positive. So we are doing that, and that lets us do this nice formulation. It is quite a bit smaller than exponential. There are NP, integer variables, assuming these are roughly the same size. N choose 2 p squared continuous variables should be there. So that's how many there are of these. And n plus n times n minus 1 p squared constraints. I mentioned dimensionality a little bit. The only place the dimension of the problem comes into our pricing problem is here in these products of x's, which you do not need to recompute on each iteration. So we can kind of do that once and then only update based on the y's on each iteration. And so in our experiments, we again saw that as the dimension went up, our average pricing solving times stayed very much the same, mostly dependent on these sizes rather than the dimension of the problem. It does take a while, though, for our more complicated mixed integer program to beat this search of the vector. We are now able to make it up into much larger variable sizes than the earlier experiments. We are getting these sorts of average times for that straight search of the reduced cost vector. And as we get to those very largest problem sizes, the mixed integer program is starting to perform faster. But its real strength really lies in that scaling up in higher dimensions. Any questions on the MIP? Yeah.
Yeah, flip flopping from like 93 to 110 Is that from what's causing it?
I don't.
I'm not sure. Okay. Wasn't sure if there was a.
So there's some luck involved, I would say, in solving these. Sometimes you get a really good new variable early on, and then it goes faster. There's also some complicated things in solving an integer program happening behind the scenes that we cannot control. We are running these experiments using Gurobi, and Gurobi does not let us see what it's choosing for branching strategies and things like that. So we have somewhat limited control over how it's solving this. All right, I wanted to end with the other linear. This is not the only one for solving the barycenter problem. It's the one we've been working on a lot because it's better suited to the general setting. But this one was actually the first one I learned. And as we're thinking about circuits, it's possible that actually this one would have better geometric structure than the other. So I wanted to mention this one. So instead of thinking about the combinations, this model introduces a variable for each of the potential support points. So this, in the worst case, is as big as the number of combinations. In the grid setting, it's much smaller. For each potential support point, we're going to introduce a variable that's how much mass we're going to put there. ZKs. Notice the ZKs do not appear in the objective of this particular linear programming formulation. They instead appear here in the constraints. So I kind of think of this like a linking variable. It's linking together the different transports. So that's what Y is representing, are the transports from a particular support point indexed at K to the destination point in the measure I. So this is really based on the transport plan of, okay, if I put mass here, where should it go? The total of those has to be the same as what the barycenter can carry, and also the same as what the measures can receive. So by balancing what's coming out from your barycenter and what's going into your original measures, you can produce that barycenter. This formulation is using the other version of the cost function. This is your barycenter point. These are your originals, but this is equivalent to what we were using in the other. And that is it. Thank you very much.
Thank you. Are there questions on Zoom? Okay, let's move to the room then. Questions in the room?
Yes.
Said the very part like all of the fixed dimension. What how bad is it dependent on the dimension?
How bad is it? I don't know off the top of my head.
Ah, it's a complicated question. I think
Yeah.
what they were the technology that they were using to prove polynomiality in dimension 2 or in fixed dimension is some power diagram structures, so some cell decompositions, and describing them grows rapidly, but we have to take another look at what factor. So the technology is computational geometry and power diagrams to get that fixed dimension result, and I'm not entirely sure about the growth in the dimension.
I don't know either. But their proof also depended on the ellipsoid method. So in terms of practicality, I think we can still improve. Like I mentioned, I think there's a lot of geometric structures still to be exploited. They've found one that is theoretically efficient. So it makes me very hopeful that there's more structure that can be found.
More questions? I think I would like to ask one.
Okay.
In Jesus' talk yesterday, you saw these three-way transportation polytopes. They sound really like special cases of multimarginal optimal transport, right?
They did.
Yeah. Okay, that's not probably way too much of an insider discussion that we're having here.
But I would also say a lot of the discussions have been around 0-1 solutions. We're backwards from that. We have 0-1 constraint matrix and fractional solutions.
Oh, that makes sense. And we have one margins here, but we scale way higher than the three. It's way more measures that are being combined. Okay, so it's a different kind of. Okay.
Exactly. So again, I think our structure can be or has a lot of potential, but it's backwards.
Okay.
Yeah.
Okay. More questions? Okay. That's it. Thank you. Thank you again, Peter. We're very much looking forward to your talk about the slack realization space of a polytope. Please go ahead.
Great, thank you so much. So yeah, we're gonna take a little bit of a departure, I think, right now into the world of realization spaces. So let me tell you what my plan is for the talk. I'm gonna tell you what a realization space is. And then I'm going to talk a little bit about the different ways that we can represent this space. So one of those will be the Slack realization space from the title. And one of the things I will also talk about is relaxations of this space that have nice algebraic descriptions, but still contain important information about the polytopes that we're studying. Okay. I'm going to try and do what every talk tries to do, which is try and convince you that my work is interesting, right? So I'm going to tell you some of the things that we can do with this Slack realization space. One of the things also notably absent from my talk is circuits, okay? So your assignment for this talk is to figure out how the study of realization spaces could inform the study of circuits. Okay, so we heard several times yesterday how circuit diameter and circuit walks depend on the realization of the polytope that you're looking at. Okay, so it makes sense that studying realization spaces could potentially help us there. And then if I have time, I'm going to tell you how we can improve the Slack realization space and come up with, let's call it an even better Slack realization space. Okay. So let's dive in by getting all on the same page. What do I mean by a realization of a polytope? So when I say polytope in this talk, I'm thinking strictly about its combinatorial structure. Okay, so I'm going to give you a collection of V vertex labels, and I'm going to organize them into facets, and that's going to be my polytope. Okay, you can think about this as an entire face lattice if that is more your thing. So if I was talking about a pentagon in this talk, I would be thinking about just vertices labeled 1 through 5, and I've organized those vertices into 5 sets, which make up my facet. Okay. These things, of course, come also with a dimension. We're going to assume that that's given to you, but you can also figure it out from the face lattice. And then a realization of your specific combinatorial type is the thing that you picture when I say the word polytope. Okay, it's an assignment of coordinates to each of those vertices so that when I take their convex hull, that's the facial structure that I get. So here, my example of the pentagon, I've given these set of 5 coordinates to my 5 vertex labels, and I do indeed get facets 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1 when I take the convex hull. Okay, so polytopes are just abstract combinatorial structures, and realizations are concrete geometric objects. And then for technical reasons, when talking about these realization spaces, it's a little bit easier to think about these things as cones. So every cone in my talk is associated to a polytope, so you can think about these things interchangeably. Combinatorially, they look the same. A cone over a pentagon has the same combinatorial structure. It's just that now I'm allowed to choose vectors that I'm going to take the conical hull of instead of taking the convex hull of some vertices. Okay. Okay, so now that we know what a realization is, we can talk about a realization space, which is probably exactly what you expect it to be. It's the collection of all the realizations of some fixed combinatorial type. Okay. And so different realization space models allow us to choose a consistent way to represent our realizations so that we can study the structure of the space and so that we can answer questions about these polytopes using this realization space. Okay, so we can choose different ways to write down an instance of a particular polytope, and that's going to lead us to these different descriptions of the space. And like I said, I want to talk a little bit about some algebraic ways to describe this space and some algebraic relaxations. And so this is going to depend on how we choose to write these things down, and I'm going to talk about 2 main ways. Okay, so one is sort of the very intuitive way, which is what I showed you in the previous slide in the definition. I'm just going to write down all of the extreme rays of the cone that I've chosen as my realization. And then the model from the title, the Slack realization space, here I'm going to be recording Slack matrices, and I'm sure some of you are familiar with these, but for those of you who aren't, I'm going to talk about those in a little bit. And then, like I said, if I have time at the end, I'm going to show you how we can actually improve this Slack realization space even further by actually combining these 2 perspectives into something we call a reduced realization space. Okay, this is going to make our model sort of more computationally efficient. So let's start by diving into the classical model. Okay, so like I said here, I'm going to think about a D+1 dimensional cone, and I'm going to record a realization by the extreme rays. So I'm going to write those extreme rays as the rows of a matrix. So here, I'm always going to be drawing my cones as the slice at height 1, again, because I'm always associating them to polytopes. So this is the slice of this realization of my cone with these given coordinates. And then the realization space is just the collection of all of these matrices that give me this particular cone structure. Okay. But the important question here is, if I just hand you a matrix, how do you know if it's the realization of the particular combinatorial structure that you are interested in? What conditions need to be satisfied for that to be true. Okay. Now, often in doing this, we want to consider certain realizations as being equivalent. I know that's dangerous in the circuit world, but I said there are no circuits here, so we're going to do it for today. So I'm going to do this by fixing some of the rays. So here I've fixed the vectors for rays 1, 2, and 5 in my matrix. And now I'm just going to vary the rays for 3 and 4. Okay, so visually we can sort of see where in this picture we need to place 3 and 4. Algebraically, we have this description via inequalities of where we can actually place these rays in order to get the facial structure that I want. And of course, these constraints are coming from the convexity of this cone, right? So if I look, for example, at the facet 2, 3, I want all of the other rays of the cone to live on one side of it. And in particular, I'm going to insist that it's the positive side of that hyperplane, right? So in particular, the ray 5 has to live on the positive side. And that particular condition gives me the A plus B is greater than 1 inequality in this description of my space. All right. And where these inequalities actually come from, or one way we can consider them, is they are determinants of the maximal submatrices of my realization matrix. Okay, so the A plus B greater than 1 is the condition that the 2, 3, 5 submatrix determinant needs to be positive. Okay. And it turns out that these determinantal conditions are what you need to describe this realization space. Okay. So my classical model records matrices of extreme rays, and these realizations are characterized by particular signs of the determinants of maximal submatrices. And the conditions are the following. So if I have a collection of rays that live inside a facet, of course, that means they live in a lower dimensional space. So that determinant should be 0. And then as we saw with the collection 2, 3, 5, if I have a collection of rays that index what we called a facet extension. So here, what I mean is I'm going to have D rays that span my facet, like 2 and 3 determine the facet 2, 3, and then 1 ray which is not on that facet. Well, that ray needs to be on the positive side of the facet, so this determinant should be positive. Okay, and so what this theorem, okay, it's not really a theorem, it's sort of a summary of a few theorems. And what it says is that these conditions are actually sufficient to tell you when you are looking at a realization. So these conditions actually give you all of the elements of your realization space. Okay, and okay, I lied a little bit. So I'm telling you about the classical model. Of course, we were not the first ones to study the classical model of realization spaces. So this theorem isn't really saying that we were the ones who determined that this was a realization space, but we sort of moved to thinking about this in a different setting, which is what I have written here. So I actually want to think about these matrices instead as points in the Grassmannian. Okay, if you like the Grassmannian, great. If you don't, we're just thinking about taking a matrix and replacing it with its column space instead. Okay, so this is really the Grassmannian model. And now instead of matrices, I'm thinking about D+1 dimensional subspaces. And instead of determinants, I'm thinking about them as Plücker coordinates, okay? And otherwise the conditions are all the same. Okay, so what we showed is this is a realization space. And additionally, it's the positive part of an algebraic variety. So this is the relaxation part that I was talking about. So we have this positivity condition, certain Plücker coordinates, certain determinants need to be positive. Okay? But if we drop that condition, then this set that we're looking at has the nice structure of being an algebraic variety. So it is the set of common zeros of some collection of polynomials. So we have a bunch of equations that we know that describe this space. Okay. And we call this the Grassmannian variety of our polytope or cone. Okay. Okay. So that's sort of all I want to say about this model. It is a nice model in the sense that it's particularly intuitive to write down. It's less nice in that it's hard to compute with. So I didn't talk about what the actual equations are that go into describing this, but they do tend to be a little bit difficult to compute in terms of interesting examples. So we're going to move over into the next model. Are there any questions up until this point, though? Yeah, Alex.
Is this an example of a positive geometry?
A positive geometry. That's a good question. I am not entirely sure. Yeah, I have not thought about that, so I do not know. Other questions? Okay. So the next model I want to talk about is the model from the title. So this is the Slack model. And here, instead of just writing down extreme rays of my realization, I'm going to take into account both the ray and facet data, and I'm going to put it into a matrix, which again, many of you may be familiar with. These have applications into extended formulations that we saw yesterday afternoon as well. So what this matrix is it has one row for each vertex or extreme ray, and one column for each facet, and you evaluate the facet inequality for that column on the ray for that row. Okay. And again, by convexity, we write all of these facet inequalities so that they're non-negative. So this ends up being a non-negative matrix. So here, yes, I said this already. So here's my example. Again, for the cone over the pentagon, I took the same realization matrix from the classical space. So you can see how there's a correspondence here between these classical realizations and the Slack matrices. And then I have this matrix of facet normals. So again, if I look at my friend, the 2, 3 facet, its normal is given by this second column. Okay. And so then I evaluate that on each of my rays. And if I start by looking at evaluating it, of course, on 2 and 3, it's in that facet. So what I'm going to get is I'm going to get the zeros in that column in those rows of this matrix. Okay. And that's the only time that I get zeros here. So in fact, you can read off the combinatorial structure of your polytope by looking at the zero pattern of a Slack matrix. Okay. Okay. And then additional information about these Slack matrices, because just like with the classical model, we want to characterize when, if I give you a matrix, are you looking at the Slack matrix of the cone that you're interested in? Okay. So another property that these matrices have are that they have rank D+1. So these rays span a D+1 dimensional cone. So that's where this rank condition is coming from. And then another nice property is that they not only capture the combinatorial information, so that we get the combinatorics from looking at the zero pattern. It really also preserves the geometry of your realization. And by that, I mean, if you look at the rows of this Slack matrix as vectors in a higher dimensional space, you get a cone which is equivalent to the cone that you started with. Okay, there's a transformation that takes you, of course, between these two cones. You're just living in a higher dimensional space.
This is an extended formulation?
It's not, yeah, you could think of it as an extended formulation, essentially. Yes. Yeah, exactly. you're going to have the exact same combinatorics. So it's not, in the sense of an extended formulation, you're very often sort of changing the number of facets, which is sort of the point. Here, the only thing you're changing is dimension. So for whatever that's worth in terms of extended formulations. Yeah. And then there's a result due to Gouveia, Grapp, Keibel, Pashkovich, Robinson, and Thomas, that if you have a non-negative matrix that has these two properties, so it has the correct zero pattern and it has rank D+1, then it actually does correspond to a realization of your cone. Okay, so like with our previous model, we're recording realizations by a particular matrix. Now we're having these realizations characterized by zero pattern and rank. Okay, so here the description of my set is that the rank can be at most D+1. The zeros are indicated by whenever a vertex or extreme ray lives in a facet, and otherwise I have these positivity conditions. Okay. So this sort of amalgamated theorem, again, is much the same as the last one, which is telling you that these conditions actually do capture exactly realizations of your cone. And it is, again, the positive part of an algebraic variety. So if I drop this positivity condition, then this set is, again, the collection of common zeros of a set of polynomials. And it's what we call the slack variety of a polytope. Okay, and I will be interested in showing you now the defining equations for this slack variety, because those are the things we're actually going to compute with in order to answer questions about these polytopes. So it's actually not too hard to capture these two characterizations in equations. So the first thing that we want to do is we want to get the correct zero pattern. And we just do this by forcibly creating the zero pattern that we want from our combinatorics. So here I've put in the zero pattern according to my pentagon, and everything else just gets distinct variables. And so as long as I plug in positive values for those variables and I can impose the correct rank, then I'm going to be happy. Okay, so next I need to impose the rank. And the way I'm going to do this is using the characterization of rank, which is the largest submatrix with non-zero determinant. Okay, so I want rank D+1. So I want all of the submatrices of size D+2 and larger to have zero determinants. So I take those collection of determinants that I compute symbolically, and I throw them into this ideal. Okay. And it turns out if you do that for this pentagon, you end up with 25 generators whose common zeros, right? So the variety associated with it tells you about all of the ways you can realize a pentagonal cone. Okay. So in particular, this is sort of a restatement of the part of the previous theorem. If I take all the variables here to be positive, in this variety, then I get the realizations that I'm interested in. Okay. All right, let me tell you a sort of brief summary of some of the things that we're able to do with this Slack model and why I think it's cool. So it does give us this nice algebraic representation of the space. So this relaxation, we're able to study using algebraic geometry, commutative algebra, and a lot of the information about the realization space it is preserved when you study this whole relaxation, which is nice. It's also invariant under duality of your polytope or cone, right? So you get the same variety, whether or not you're looking at a polytope or its dual, which is kind of a fun feature. Like I said, it provides us a computational way of actually answering a bunch of questions about polytopes. The biggest of which I would say is realizability, which means if you hand me a particular facial structure you want to know whether or not there is actually any concrete realization of this thing at all. And this is also related to some of the things we heard yesterday a lot about the Hirsch conjecture. So Paco Santos and his PhD student actually created a bunch of non-D-step prismatoids in 5 dimensions. It was some sort of topological construction, so they didn't know if these were actually corresponding to concrete polytopes. But if they did, they would be the smallest known counterexamples to the Hirsch conjecture. So he sent them to us and he was like, are these really polytopes? And we haven't looked at all of them yet because there's 4,000 of them. So I have an undergrad working on that this summer. But for the few that we did start looking at, we actually were able to show that none of them are actually realizable as polytopes. So no new counterexamples as of yet. Okay. It allows us also to do some theoretical classification. Answering whether or not, or classifying, I should say, projectively unique polytopes. So what this means is that all of the realizations are basically related via some projective transformation of the underlying space. So you effectively have one realization. Classifying those is a notoriously difficult problem, but we are able to identify a certain subset of projectively unique polytopes using properties of the Slack ideal. And then these were actually initially introduced to study PSD minimality. So like extended formulations, this is discussing when a polytope has a small lift, now not to another polytope, but to a semi-definite set. Okay, so now you can do semi-definite programming efficiently over this lift. And this Slack ideal provides conditions and obstructions to when a polytope has this nice form. Okay. But as with most things, it is not without its struggles. So the problem with the Slack ideal is that for many interesting polytopes, the Slack matrices are just too big for us to actually calculate the full ideal. So as an example, here's a nice polytope from Grunbaum's book on convex polytopes. It's 8-dimensional with 12 vertices and 34 facets. And this is sort of a schematic of the 0 pattern of its Slack matrix. And if you try to calculate the Slack ideal of this thing, your computer, or at the very least my computer, died multiple times. Okay. But in Grunbaum's book, they study this polytope using combinatorial techniques, and it has a lot of interesting properties. For example, it can't be realized with rational coordinates. It is projectively unique, and it has something called a non-prescribable face. So if you pick a bad realization of a particular face, you can't actually complete it to a whole polytope. Okay. So how do we solve this problem? We would love to be able to, at the very least, do things that are already known about polytopes with this new mechanism. And so the way we're going to do that is we're going to use the following theorem. Okay, so what we showed is that not only are the realization spaces equivalent, of course they should be because they should both describe all realizations, but these algebraic relaxations, the Slack variety and the Grassmannian variety, are also equivalent, right? And the way that we prove this is by providing explicit maps. And these explicit maps allow us to parameterize the Slack variety in a nice way, describing all of the entries of the Slack matrix in terms of the entries of a smaller portion of the Slack matrix. Okay. And very roughly speaking, the maps are that from the Slack model to the Grassmannian, we're going to just take the column space of the matrix. Okay. Going from the Grassmannian to the Slack model. So in the Grassmannian, what we record are these Fluker coordinates, the determinants. And as it turns out, you can think about the entries of a slack matrix as being calculated via these determinants. So all you're doing is filling in Flickr coordinates in the correct spot in your matrix. Those are the maps. Okay. So the solution here is to only keep the part of the slack matrix that determines the equivalent point in the Grassmannian model, right? You don't need a whole matrix to determine its column space. You only need the right number of linearly independent columns. Okay. I should have had these up earlier to remind you what these sets are, but in case you've forgotten, they're here now. Okay, so there's our subspaces. Here's our matrices with the correct rank and zero pattern. Okay. Okay. So we have our full slack matrix. And what we want to do is we want to keep only the full rank portion of it. Okay. This is easy, of course, if you have an actual concrete slack matrix, but the trick here is that we're doing this symbolically. We want to keep the full rank symbolic portion, but it actually turns out that you can use the combinatorics of K to identify the columns that you need to keep. And for the sake of time, I will not tell you about that today. And then in addition, you do actually want to keep columns that correspond to non-simplicial facets, so facets that aren't just simplices. Okay, so we might have to extend this matrix a little bit. That allows us to complete this matrix uniquely from the information that we have here. But now we have this smaller matrix that we are going to take the slack ideal of. So we call this the reduced slack matrix and the reduced slack ideal. Okay, and just to show you that this does indeed work in some nice cases, we're going to go back to this example, which started off looking like this. And when we look at its reduced slack matrix, we're now down to, from 34 columns, only 13. Okay. And before my computer died, even trying to calculate this ideal, now I can put the ideal on the slide for you. Okay, I cheated a little bit. There's some ones in here where variables should be. We're always allowed to sort of do that to a slack matrix. Again, something I will not talk about today. Okay, it's a really nice ideal, and we're able from this ideal to recover all of the information about this polytope from Grunbaum's book. Okay, so in particular, if we factor the only quadratic in there, we can see that none of our realizations could be rational, right? If you have a rational realization, the slack matrix is rational. Okay, so Jesus is really unhappy right now somewhere. So this has no rational realization. There are two projective equivalence classes. So by setting some things to 1, I'm essentially looking at an equivalence class of representatives here. I now complete this matrix back out to the full thing using my maps from the Grassmannian. I see that one of them has negative entries, so that's sort of an artifact of my relaxation. I just throw it out. The other one actually corresponds to the unique representation of this polytope. Okay. So with that, a quick recap. So we can see the importance of how we represent realizations. It changes the algebraic description of our space. We like this slack perspective. It allows us to study realizability, projective uniqueness, PSD rank and minimality, and more properties of a polytope from this algebraic perspective. We can take advantage of explicit maps between realization space models to help us exploit the strengths of each of them. And then by doing this, we get this reduced slack model that makes previously intractable problems possible. And so I should also say that it was this reduced slack model that allowed us to answer the questions about Paco's prismatoids that he sent us as well. So future questions, there's many of them, but I will only put one up here today, and I will throw it out to you guys. And with that, I would like to say thank you for your attention.
All right, questions from the Zoom audience?
I have a question.
Yes, Jesus, hi.
So hello, I mean, first of all, let me maybe start with a bit of a historical comment. I mean, Bukowski, your academic grandfather, Sturmfeld, I mean, Grove-Pluker coordinates in the 80s, right? I mean, I just want to say that the Grassmannian model is not that new.
No, correct.
Yeah, I just want to make sure that the references there are a little bit more actualized.
Yes.
But I mean, the main question is in the model that people study in the 80s, I mean, the Grassmannian model, a lot of things were proved regarding complexity. For example, the realization spaces, disconnected realization spaces. Can you prove the same thing from this model? Or if you prove one thing for a model, can you get it for the other? Is this a reciprocal phenomenon?
That's a really good question. So that is sort of one of the things that falls under future questions. Yeah, so there are these results about sort of interesting realization spaces of certain polytopes. Like, for example, as Jesus said, some of them could be actually disconnected spaces. And we do not know if that carries over into the SLAC model. So yeah, we know that these algebraic relaxations are equivalent, but it's not clear that the maps preserve these other sort of properties or structures of the spaces. So I would say that's definitely a question for future study, is whether or not properties like universality, for example, as well carry over into the SLAC model.
Thank you.
Yeah.
Questions from the room?
Yeah.
Here's not a question, but I just really liked your slides. I thought they were really, so
Thank you.
little pointing things were super helpful and stuff.
I'm a very visual person,
Same.
so I like to lead people through
Yeah.
my slides
Yes.
the way I need to be
Yes.
led through
It's
slides.
really helpful, and like that's something I might try to do moving forward. Yes, yes. But also a great talk.
Thank you. Yeah, Damon.
So does this premise also then kind of force us to acknowledge irrational circuits?
That's a good question. I guess maybe it does. Yeah. It is definitely an example of a polytope that can't be realized rationally. So I suppose if you were doing anything with circuits of that polytope, you might have to acknowledge irrational circuits. Sorry, Jesus.
It's fine. It's just that you never find them in nature so often, but it's okay.
Let's thank the speaker again. All right, we're ready for our second talk of the pair here. This is Michael Weigel, and he's going to talk to us about the hardness and approximations of submodular minimum linear ordering.
Okay, hi, thank you for the invite. This is a project started a few years back at Georgia Tech, and now in a couple months, none of us will be at Georgia Tech. And unfortunately, there'll be circuits in this talk, but not the circuits we've been seeing, so sorry. So here's a motivating example. Suppose we have a list of integers, 1 to 2 to begin, and we want to communicate over a binary channel. And what we want to communicate is a function, bijection between these integers. But we have the possibility of a bit being flipped in error during communication. So this is like a communication theory motivated problem. So how can we model this? And we want to minimize the expected error, or the same as the aggregated error. So we can model this as the graph, the n-dimensional hypercube. And we're going to let pi be an ordering on the vertices, or a bijection. And our objective is to minimize this sum, where for each edge, we minus the 2 labelings, and we want to minimize over the expected difference over each edge. And this was known in 1964 to be solvable in polynomial time. And this is the first instance of the MLP framework I could find in the literature. This is now called the minimum linear arrangement problem, which is very well studied for different graph classes. Here's another motivating example. Suppose we have a network represented as a spanning tree of a graph. And then we have this possibility, maybe imagine it's like an electric grid or something, and we have this possibility of an edge failing, and we have to repair it with a new edge. What is the catch here? We want to do this autonomously. We don't want to have a control room controlling this. We just want each edge smartly to do it on its own. The solution is we give each off-tree edge a unique waiting time. And then we wait a certain amount of time, and the network isn't repaired, then the edge would know it needs to activate if it's designated at that time, and it can repair. And so the question now is, what order do we give to the off-tree edges to minimize the expected waiting time? So here's a picture, probably easier. So here is an ordering we give to the off-tree edges, 1 to 5. Oh no, this edge failed. And so we wait 1 unit of time. This guy would check, see if he could repair the damage. He can't. We'd wait another unit of time. The second edge would check, and so on. And this would continue to 4 units of time. And then we would repair the network. And the score would be 4 here. This is the minimum reconnection time problem. This was introduced by Swati and some of her students. In general, there's this, you could add weights to things, make it more complicated, and the motivations for robustness of electric networks. And this was shown to be hard.
Sorry, but this is taken among all possible edges of the tree that tree?
Yeah, so we had the original tree, and then a random edge would fail.
Random edge. Oh.
Uniform. Maybe you can even do other probability distributions, but uniform. Okay. And so we have 2 different problems. One's motivated from coding theory. We know how to solve in polynomial time. We have a different problem motivated like we're trying to solve catastrophe of electrical network, and that's NP hard. So the main question is why? Why is the first one hard and the second one isn't? And that's the main motivating question of our project, to understand which ordering problems are hard and which ones aren't. So here's the general framework for the minimum linear ordering problem. Is you have a set E, a set function, an output is an ordering, and you minimize the prefix sum, the prefix. So you pick an ordering and you take the prefix based on respect to the ordering. And this is not strong enough to capture every ordering problem. For instance, I don't think this captures TSP, at least I'm not aware, but it captures a lot of problems. And so it generalizes many different problems. And so what the goal now is to understand how properties placed on the function f affects the hardness and approximation. So we want to study this problem in general, not just for any particular problem. And I should maybe say that this problem was introduced back in 2012 by Awada, Tripathi, and Tale, I think. Okay, so a function is symmetric if the set function is equal to its complement. Submodular is well known and well studied. Has many different applications. It's like a discrete analog of convexity. It makes optimization possible, so on. And a function supermodular, negation is submodular. And a function is monotone. So these are natural general properties that many problems will fall into. And we want to understand which of these properties are difficult and which of these properties are not. So here's a table of results for different problem classes. On the left is the function class, and the function names in the middle, and the hardness. And you can see it's generally pretty difficult in terms of NP hardness. And our contribution is the problem in red. So the natural thing we first looked at is matroids as their integral monotone submodular functions. They have a nice structure, they have nice properties. It might be a natural guess that maybe these are easy to solve in an LP framework. And so a pair is a matroid if you can define them in like 10 different ways. We're looking in terms of a rank function because that's what we're optimizing over. It's natural in this setting. And so we can define independent sets in terms of the rank function. And an independent set is maximum, we call it a basis. And so matroids were well studied for a long time now. They generalize linear independence in terms of vectors, linear independence in terms of graphs. And we would expect this to be reasonable because they have this nice property. When you add an element to your set, you can increase the function value by at most one. So it's not variable, it's nice structure, combinatorial structure, it should be exploitable. And so unfortunately it's not, and I'll quickly tell you why. There's a very easy proof that we stumbled upon. So you let A be a matrix over a field F. And so a vector matroid is exactly generalized linear independence in a vector setting. So we let the vector matroid designate by this. And the rank function of the vector matroid corresponds to the rank function of the matrix. And the uniform matroid is simply the matroid on M elements, such that every set of size K is a basis. Okay. And the uniform matroid isomorphism problem is the following. Basically given a matrix, is it isomorphic to the uniform matroid? And this problem was NP hard by Oxley and Walsh, which took some time to find. And so matroid MLP, you're doing MLP with the rank function of a matroid. And it's a very easy reduction because basically the optimal objective for the uniform matroid is unique. And so if you could have an algorithm to solve matroid MLP, you could identify a uniform matroid. And that's it. And so it's a very disappointing result as it's a 2-line proof. Any questions so far? Okay. And so the next thing we looked at was graphic matroids. And so now we assume even more structure. You have a graph. And so we let MG denote the graphic matroid, and it's a set is independent if and only if it has no cycles. When the bases are being spanned for, so G. And the rank function is simply the maximum number of edges you can add. That doesn't include a cycle. And this is natural to look at because not all matroids are graphic. For example, most uniform matroids are not. And so that avoids the silly proof from before. Goal, spoiler alert, it's NPR as well, but it's very non-trivial to show now. And here was the reduction map. And so min sum vertex cover was previously studied in the literature to be hard. It's kind of an aggregate cost on vertex cover. MLVC is min latency vertex cover. This was introduced during the reduction. And weighted graphic matroid MLP is you just add weights, and if the weights are size bounded, you can reduce it in polynomial time. So here's the min sum vertex cover problem. Given a graph, and you want to minimize, it's like the minimum arrangement problem. Now you take the minimum instead of the absolute difference of the two labelings. And so you're looking for the smallest time that an edge is covered. And so this is like an aggregated cost of vertex cover. An example of supermodular MLP. And it was introduced and used as a heuristic for semi-definite program solvers. And unfortunately, it's NP hard to approximate and solve. Min latency vertex cover is a very similar problem, but now instead of the min, you're taking a max. And MLVC is an example of monotone submodular MLP. And monotonicity was pointed out by an anonymous referee during the publication process, so give credit where credit's due. And so here is the theorem relating the two problems, is that they're related by a linear shift in the sense of the min latency vertex cover on a graph is equal to the min sum vertex cover on the complement related by this linear shift, where n is the number of vertices of the graph. Proof sketch. Well, I just said it. And if you have an ordering on the graph, the reverse ordering is minimizes the dual problem on the complement. And so corollary, we have that MLVC is NP hard. And so I showed this part of the proof. And I won't talk about the rest. So with a bit more work, we have great graphic matrix NLP is NP hard as well. And so we introduced min latency vertex cover. Next question asked, well, it's hard. What can we do to approximate it? Natural step is to X. The big idea to approximate it is that we can reinterpret it as a scheduling problem. If you don't know what this notation means, that's okay. I don't either. It's from the scheduling literature. And this is well studied, but in a certain what it essentially is you can interpret it as a scheduling problem on a single machine with precedence constraints. With precedence constraints, you get a post set. And so you can, if you look at the fractional dimension, if it's small enough, you can get a nice approximation on the scheduling instance. And so how do you define fractional dimension? You define it in terms of a set of linear extensions, which we call k-fold realizer, such that for any incomparable pair in the post set, it's in at least k linear extensions. This is the combinatorial logic used to define the fractional dimension. And so an older result in the literature is that the scheduling instance can be approximated 2 minus 2f, where f upper bounds the fractional post set. And as long as your post set bounds the fractional dimension of the post set, which is a typo. But as long as your post set is not a linear order, it has incomparable elements, f is at least 2, so this bound makes sense. And so to use this technology, we need to construct an efficient sampling algorithm for the k-fold realizer. And we did that. And so what's the method to do it? You just choose a random ordering, and that does it. Which is surprising for these type of problems. Generally choosing a random ordering is bad. And this generalizes in terms of the hypergraph analog as well. Okay. Everybody else was putting linear programs, so I tried to fit this in. And so for the min latency set cover, it has a natural linear program. For each edge, you have an uncover time. And so for each edge, we want to uncover it fast enough. So this is the objective function. Each vertex in each discrete time has a variable. And so you can cover each vertex once. And this constraint is just saying you can only uncover an edge when all its vertices have been uncovered. And so this is a very natural LP. And we have a matching integrality gap for the LP reaction station for the min latency set cover, lower bound, I should say. For an upper bound, we had to assume deregularity to get the matching integrality bound. And an open problem for this problem is, do we really need deregularity to get this integrality gap? Last class I want to talk about is monotone cell modular, which is previously well studied. There was a 2 approximation known prior in the literature. How they achieved this was they They look at the permahedron, they take a low loss extension over it and do some rounding. And the question is, can we do better? A little bit. And so we gave a slight refinement on this bound. And so the proof technique we used was theory of principal partitions of some modular functions, which is this very old technique from the literature of submodular optimization. And what we've later found is that this technique has been previously used for a more general problem, which is submodular search problem. And they used a very similar technique in a very different language though. But their analysis was based on the curvature of the submodular function. And basically they also give a two approximation in some settings, but for certain submodular functions our bound does better, for certain others theirs does better. They had a question of, does their technique beat the Iwata bound? Is it a pure refinement? With our analysis, we can say yes now. And so here's a list of open problems related. Is minimum linear arrangement, which was the coding theory problem from the original, MLVC, MSCC for regular graphs, they can all be related by linear shifts. So the question is, if for regular graphs, is it NP hard to solve? To solve an LP relaxation for MLVC provide a 4/3 approximation. We don't know this. We know this if we assume regularity, but okay, we want it for all graphs. And the more general question for hypergraphs. And I would find a very interesting question is what parameters characterize when MLP is hard in terms of submodular functions. A better question is, does this question even make sense? I don't know. But it would be nice, instead of looking at individual problems, to say this is hard, this is hard. Is there parameters on like how complex a function can look? And we know if this is NP hard or not. Okay. Conclusion. Thank you.
All right, again, questions from Zoom. Questions from the room?
What was specific about the cactus graphs that made it not hard? Like,
Yeah. It's not too interesting. So you can basically, you have a cactus graph and they have different links. And so it's just like, let's say link 10, link 7, link 6, 5, 11, 3, and then you just greedily grow based on the links. And so, I mean, it takes some analysis to see this, but it's just like a greedy algorithm based on the type of links.
So could you do that for like any connected graph then? Like using that same kind of greedy, like just grow out the years or whatever, you're to like do your thing.
So I'm skipping a lot of technical details, but for matron NLP, you can take a new interpretation of like, you first choose a basis, you first choose a spanning tree. And then for the fundamental circuits of the graph, you order the element, you pick an ordering on the basis, and then the fundamental circuits take like a score based on what elements they see in the tree. For this, the trees are very simple, right? They're not going to interact in weird ways. Okay. So in this setting, it doesn't matter which tree you pick, so that it avoids a lot of the combinatorial explosion of what can happen there, which makes it polynomial.
Yes. A question regarding the approximation factor that you get. What is the approximability that you know? Like, can you hope to get betas, or it is a big sum?
It's approximation hard.
Sorry, it is a big sum.
Yes, I think there's some information theoretic type lower bounds ballooning in the literature. For which question though? I mean,
you show some constant factor approximation.
I think monotone submodular, I believe there's something in the literature floating for MSVC, it's approximation hard. MLVC, I don't know. Minimum linear arrangement is approximation hard, I believe. I think there's some hardness results. So yes, for most of these, they're approximation hard. I don't think you should expect a yes. Yes.
All right, let's thank the speaker again.
Welcome to the last session. The next speaker is Weston, who will be speaking about diameters of parallel and series connections. Go ahead.
Okay. All right. Well, I'm going to bring us back to true polyhedral theory. We'll be talking about diameters. This will be a little bit faster. I'm going to go through the background quickly because so many other talks have already covered it. Yeah, so first, the diameter of the graph is just the maximum distance between any pair of vertices of the graph. And this is going to give rise to the combinatorial diameter of a polyhedron. So given any polyhedron, we can derive a graph from it called its skeleton just through its vertices and edges. And then we say the combinatorial diameter of a polyhedron is just the diameter of its skeleton. Okay, so, and then just to cover some past results, we have some bounds in general for polyhedra. We don't know if they're actually great or not. We know that it's quasi-polynomial in the number of facets and the dimension, and it's also polynomial in the dimension and the maximum absolute value of its subdeterminant. But we also have stronger bounds for many classes of polyhedra, such as 0-1 polytopes or network flow polytopes. Those are in fact bounded by n minus d, or f minus d if we're using f for a number of.
Can I ask something right away?
Yeah.
0-1 polytopes, that's also the bound of, right? That's an induction-based argument.
Right.
Right. Okay, so
Right.
it's both. Yeah. Okay, good.
Yes.
Thank you.
In fact, I'm leaving it as n minus d right now to connect to this, to the famous Hirsch conjecture, which several other people have brought up many times. And it just states that if we have a d-dimensional polytope with n facets, then we ask, is the combinatorial diameter at most n minus d? And this is indeed false. Yeah, so Santos proved this is false, something we've known from several of our talks now. So one area of study is asking which polyhedra actually do satisfy the Hirsch bound. Because most polyhedra we look at indeed do satisfy the Hirsch bound, at least if we're generating examples on a computer and checking. These Hirsch counter examples are hard to come by. So two operations that I'm interested in would be a way to build, possibly build Hirsch satisfying polyhedra from known classes of Hirsch satisfying polyhedra. So the first operation I'm interested in is this parallel connection, where you take two polyhedra. They have a particular form, but you can pretty much reduce any polyhedra down to this form on the left and the right, and then define the operation. And the result is what we call the parallel connection of those two polyhedra. And related, we have the series connection, where we just, instead of overlaying the two ones, we just stack them on top of each other. Wait, so these are two pretty simple operations to apply to polyhedra, but what they do to the diameter is still unknown.
Okay.
Yeah. Yes, we overlay these two ones. So it's close to being a Cartesian product, but now we have that shared constraint. Okay, and series connection, again, we just stack them, we don't overlay. All right, so before diving into the parallel and series connection, I want to talk a bit about the Cartesian product and get into the proof about its diameter, just adding the two diameters together, because these ideas are going to come up for parallel and series connection. But talking about them in the Cartesian product case is a fair bit simpler. So here we're using D to just indicate diameter of the polyhedra in there. So the diameter of the Cartesian product of two polyhedra is just the sum of the diameters. And the way we do this is we show that if we have a vertex of the Cartesian product, then both X is a vertex of P and Y is a vertex of Q. So this says that the vertices in the Cartesian product are also related and can be projected to vertices of the input polyhedra. And if we're interested in constructing a path between two vertices, so if we're given two vertices xy and x prime y prime, we can first construct a path from xy to x prime y and show that that path is going to have diameter bounded by the first polyhedron, dp. We just take the path in the input polyhedra, show it exists in the Cartesian product. We're good. And then we do that on to then walk from x prime y to x prime y prime, and we get that it's bounded above by dp plus dq. Okay, so now we want to take similar ideas to this. We'll try to replicate it for the parallel connection and the series connection. So first, throughout, from now on, we'll let P and Q be these two polyhedra. So this matches the form that we wanted for the parallel and the series connection. And we're going to give these matrices names, A bar and B bar. And we're going to really overload D, but for the most part, it's just going to refer to the diameter. If we ever have two coordinates in it, which I think comes up only twice in this talk, that's the distance between two vertices. General dp is the diameter of polyhedron P. And then we have this new construction dA, which is the maximum diameter of a polyhedron with a quality constraint matrix A. And this is going to prove useful because when we're taking the parallel connection, we're going to want to be able to change the right-hand side of our input polyhedra. And so if we can say it's bounded above by dA, this will allow us to actually lift our diameter bounds. Okay, so beginning with the parallel connection, we first wanted to show that vertices in the parallel connection correspond to vertices in the input polyhedra. Now, for the Cartesian product, you always have that x and y correspond to vertices x and y in the input polyhedra. That's not exactly the case with the parallel connection. Instead, we get that if we have a vertex v, we can write v as equal to xy again. Then v is either a vertex of p, a vertex of q, or a vertex of both, but the right-hand sides might have changed. And to see why that would happen on how we're changing the right-hand sides, I'm going to go back just a few slides to the parallel connection definition. It's possible we could have a vertex of this polyhedron where we have some amount of value ax plus s plus by equals ca plus cb. If we were projecting to our vertex, we actually still keep this xs. And so this b might not be the same as that cb value. So we just have to make an adjustment of that coordinate. But that's just a small technical detail. And as long as we're using dA, then we're fine. Okay. So we've said that we can project into some vertices. They don't project both at the same time, but we'll work around that. And this actually allows us to partition the vertices of the parallel connection into three categories. And these categories are just based on, is it projecting to just P, just Q, or is it projecting to both of them? And now we'll construct a diameter bound by considering vertices where it's possible to do so in each pair. And the easiest case of this is when we're projecting to vertices that, when we have vertices that project to both vertices of P and Q. That's where it will be easy enough to take our intuition from the Cartesian product and apply it to this case. And we do some work showing that the distance of a vertex in another category to that category isn't too bad. And so to really lay out what we do, we want to talk about lifting a path. So in the same way that we had the Cartesian product, we looked at a path in P and showed that those two vertices in the Cartesian product were at most distance d of that input polytope by that path. We can do the same thing in the parallel connection. And this depends on if we have x, s, y, we count basic variables. If y has m2 minus 1 basic variables, and here we do need some assumptions on simplicity. Again, this isn't really a restriction. Then we get that the distance between two vertices is at most d of bar a. And this is going to allow us to construct a walk between two category 2 vertices. This is the category where they project to both P and Q. When this happens, when they project to both P and Q, we're able to show that x, s, y prime, or x prime, s, y is a vertex. And here, s star just means s may have taken on a different value. But, it's still a vertex. And then, based on the lemma above, we're able to show that the distance between x, s, y, and whichever one of these is a vertex isn't too bad. It's just d of bar a. And then by a symmetry argument, we get that the distance between whichever one of these two is a vertex and x prime, s prime, y prime is bounded by d bar b. We get the same result, but if we flip, we hold x fixed and we look at y, then the distance is d bar b. Same argument, just interchanging the roles of the variables. And this is what now allows us to derive a nice diameter bound for the parallel connection. So we've shown it between two category 2 vertices. And it turns out that if you have a vertex that's not one of those vertices that projects to both vertices of P and Q, then it's adjacent to one. And so we pick up a diameter bound of, apologies, this should be d bar A and d bar B plus 2. And connecting this back to Hirsch, this shows that if P and Q satisfy Hirsch, then the Hirsch bound is not exceeded by more than 3. And that's because when we overlaid those two constraints, our Hirsch bound actually drops down by 1. So that's why it's the Hirsch bound if both dA and dB had achieved Hirsch, then that plus 2 would have actually been 3 more than what Hirsch needed to be. Right, so that's the parallel connection. Any questions right now on the parallel connection, or we'll move on to series?
Is this tile? Do you have an example of this really happens?
No, we don't, and that would actually be a very interesting question to know. If this was tight and you could find that it was tight for a pair of Hirsch satisfying polyhedra, that gives a really simple way to construct Hirsch, not Hirsch satisfying so Hirsch satisfying counterexamples. And if it was tight, and then if it wasn't tight, which maybe we conjecture it shouldn't be tight, because we'd expect that such a simple operation applied to two Hirsch satisfying polytopes should be Hirsch satisfying, but who knows? Then
a follow-up question or a comment on this. So the parallel connection does capture some special cases of true sum, right? So if this is tight, would that then disprove TU Hirsch? Does that question make sense?
Yeah, yeah, I was just thinking about it at first because you get a you can, yeah, so it would disprove TU Hirsch. Yeah, I was just making sure. Yeah,
yeah. So we think this is. Yeah, I think this we don't expect this to.
Yeah.
Yes.
Yeah, I think. Yeah, I mean, based on how many weird like polytope results are out there, I wouldn't necessarily bet against that you can't find a pair where this is tight. But
To be honest, I'm going to talk about it. I didn't really mean it independently of Hirsch. Like I was thinking, do you have any examples in which you get maybe the plus two? Maybe you have it for some polytope that are not tied at Hirsch, so they do have some snap. But that was more my question.
Yeah.
Because yeah, you can see.
But,
So
yeah, we don't have any.
some polytope where maybe you are
Mhm.
way below Hirsch, so that's fine if you're satisfied, but you.
Yeah.
We also, and it is a very interesting question with some really serious
Mhm.
implications.
Yeah.
Yes.
Yeah, and there's also interesting work to still be done on this, on how we might be able to get the diameter bound a little bit lower. So when we're doing this work, we're primarily looking at the distance between vertices. This is going to use edges that actually come up in the input polyhedra. But when you make this construction, you actually get a whole bunch of other edges too that we don't use. So that might allow some sort of shortcut to get this down to being a -1 instead of a +2. Okay. So just a reminder on what the definition of the series connection is, because we just went through all of the parallel connection. We're just stacking these two matrices instead of overlaying those ones. And now throughout for the series connection, we actually need to assume that P and Q are Hirsch satisfying integral polyhedra, but this is still in line with our work trying to show that the series connection of two Hirsch satisfying polyhedra is Hirsch satisfying. Now we're just being explicit that we're assuming Hirsch satisfying. So we have a lot of similar results for the series connection that we had for the parallel connection. We can still have that if we have a vertex of the series connection, then we can project it to a vertex of P or Q, or possibly both. And again, we might have to change the right-hand side a little bit. And like the parallel connection, this is actually going to give us a categorization of the vertices. And again, just into 3 categories. And now we're also going to look at cases where we can lift walks from those input polyhedra into the series connection. And this turns out to work really nicely when your S coordinate is fixed to 0. When it's not fixed to 0, we run into a lot of trouble. So in particular, if your S wasn't 0 and you're trying to lift one of your steps, if that S coordinate changes, then that also changes what's going on in, say, the Y portion if you were looking at what's happening in the X portion. But when they're both 0, we get that the distance between two vertices where we have Y fixed is at most D bar A. And similarly, if we left it for X fixed, we would have gotten D bar B. And this then allows us to construct a diameter bound. But here we have to set S to, we define S diff to be the difference between the max that S can take on in the series connection and the minimum S can take on in the series connection. So this is where our bound does get a lot weaker, and we can actually, doing a lot more technical details, reduce this down to a quadratic diameter bound in terms of dA and dB. But for the easier bound to construct, we get dA, again, this should be D bar A plus D bar B plus 2 S diff, where S diff is now how far away we might be to walk from a facet where S is 0 or where S is minimized. And this S diff doesn't grow too badly. In fact, S diff is always going to be bounded by that corresponding different minimum of S diff for S diff if we define it for, say, P, just P or just Q. That maximum value can take on in P minus its minimum value it can take on in P. And so this also shows that if P and Q satisfy Hirsch, then the Hirsch bound is not exceeded by more than 2 S-diff. And related to Laura's question earlier, this is one that I would really not expect to be sharp here. It would be useful to figure out some ways to walk in the polyhedron where we don't have to fix S to being held at a facet. All right, so again, just some further directions that we might be able to take this research is asking if these bounds are sharp, something we've covered. The parallel connection, again, we utilized edges in the input polyhedra, but not so much about these edges that are created in the parallel connection, but might not be present in the input polyhedra. I think that this would help us improve our bound and hopefully take a shortcut in some sense. And then looking at ways to refine the technique for S-diff. One way that we've looked at, but it goes beyond the time for this talk, is being able to reduce this bound to being a quadratic bound. I'd be curious if there's a way to bring that down to being a linear bound even more. Right. That's my talk. Thank you.
Thanks a lot, Weston. We'll
thank
first
you.
open the questioning to the Zoom audience, if there's any questions.
I can ask a question. Can you comment on the connection to the total unimolar matrix classification? I mean, is the expectation that maybe this can lead to, prove that the Hirsch is true for total unimolar matrices, or what do you believe?
That's yeah. Yes, so that's actually where this was born out of. Series connection and parallel connection are the ways that come before two-sum, in a sense. You can construct two-sum from the parallel connection or the series connection. So the thought is start with the easier case, see what we can prove, and hopefully this will give us intuition on how to prove that, say, the two-sum preserves a linear bound. And then if you can say that for the two-sum and the three-sum, a few other operations, then you'll be able to show that TU polyhedra satisfy the Hirsch bound.
Okay.
We're still ways off though.
Yeah, yeah, there's a ways to go.
Thank you.
Great, you're welcome.
Any other questions from Zoom? All right, now to the audience. Laura.
So just going back to your second open question, like just to reformulate, are you asking what happens with circuits here, or edges that are not present in either? You mean circuits, like what these operations do on circuits?
So I am actually also interested in what's going on with circuits, but this is about in the parallel connection. And we're able to project some vertices into P or Q. So we're also able to project those edges and find them to lift a path. But there's also other edges present in that polyhedron that we didn't consider for constructing these diameter bounds.
Oh, I see.
So
Okay.
actually using those edges.
But say that those edges come from circuits, and knowing what the circuits look like in these things is very well known in matrix theory. Losing circuits together in the pieces in the right way.
Any more questions?
Sean.
Yeah, I apologize if you mentioned this. Similar to like where with the Cartesian project for example, we sort of know geometrically what the Cartesian product to polyhedra look like. Is there a relatively simple geometric understanding for what the output polyhedra looks like if I do these two operations, like in terms of the geometry of my original, or?
Not exactly. So not as nice of one.
Sure.
Yeah, I mean, a lot of them, if you fix either X or Y to a vertex, then that face is isomorphic to one of the input polyhedra, the other one that you didn't fix, and it might have had the right-hand side adjusted. So you have to just consider the facet being moved, which creates problems. But in general, they look pretty similar to the Cartesian product, but there's not a nice way to think about it.
But it doesn't get totally tricky compared to.
Yeah.
They're still like, I can still sort of see my original colors.
Mhm. Yeah, and even these edge directions that we didn't use, they're not too hard to visualize. It was more of a trying to show existence between two vertices that such an edge existed, where we could find, we know such edges are out there, but given particular vertices, it was hard to determine if they're actually adjacent.
There are no more questions. Let's thank Weston again. Okay, the last talk will be given by Yong Ho, and he will tell us about path odd covers of graphs.
Okay, thank you. So this is joint work with Stefan and a few other people from the graduate research workshop in combinatorics last summer. And this project was initially proposed as a purely graph theoretical problem, and it just happened that it is somehow related to the diameter of partition polytopes. Okay, so and since this is not a graph theoretic audience, I'm going to pretend that this has very interesting graph theoretic motivation. So the motivation goes back to this classical result of Graham and Pollock from 1972. So they pose this problem of decomposing the complete graph into edge disjoint complete bipartite graphs. Okay, so what is a minimum number of edge disjoint complete bipartite graphs? You need to decompose the complete graph. And they cited the motivation for this as something related with telephone circuit switching. So they were working at Bell Labs back in the day. Okay, so here's a trivial observation that you can do this with n choose 2 complete bipartite graphs just by taking each edge once, right? That's very trivial. Here's a slightly less trivial upper bound that you can do this with n-1 complete bipartite graphs. Okay, and the proof is very simple. You just take, so each of your bipartite graph is going to be a star. So you start with this one edge, that's a complete bipartite graph. You add a new vertex complete to everything else, that's another complete bipartite graph. And you just keep adding these stars, and each star is a complete bipartite graph. So you can do this with n-1. Okay, and in their celebrated proof, they show that this is actually best possible. So they show a lower bound that you cannot do better than n-1. Okay, and this is a very famous proof. That it's one of the proofs that are in the proofs from the book, and it's a linear algebra argument, and then people really like this argument. And what's interesting is that we don't really know how to prove this lower bound without going through this linear algebra, which is quite interesting. Okay, so here's so Babai and Frankel in their textbook on linear algebraic methods in combinatorics, they give this linear algebraic argument of Graham and Pollock, and they ask for sort of a binary field version of this linear algebra argument. And if you just sort of adapt it this way, then the problem becomes you want to cover each edge of the complete graph an odd number of times. So you want to find this minimum set of complete bipartite graphs which cover each edge of the complete graph an odd number of times. So this is the analogous statement. Yes, and another way to state it is you want complete bipartite graphs whose symmetric difference is the complete graph. Okay, and then just by adapting their proof to the binary field, they give this lower bound. Okay, and this, it turns out this lower bound is almost tight, so it's always at most off by 1. Okay, so it's either exactly the n/2 or +1. Okay, so this problem was generalized a bit farther. So let's say instead of oddly covering the complete graph, I give you some fixed graph. Can you give me a set of complete bipartite graphs whose symmetric difference is this given graph, and how many such complete bipartite graphs do you need? Okay, and this was considered in another GRWC project from the previous year, and they show that you get a lower bound of half the binary rank of the adjacency matrix of the graph. Okay, so that's an interesting result. So let's look at a different decomposition problem. So these are two other sort of very famous decomposition problems in graph theory. So this is the Gali's path decomposition and Hayash's cycle decomposition conjectures are both from the 60s. They're still wide open. Okay, so the path decomposition conjecture states that Every graph on n vertices can be decomposed. So basically, the edge set can be partitioned into at most half of n paths. And every Eulerian graph can be decomposed into basically half of n cycles. These are the conjectures. And again, these are still wide open, very difficult, long-standing conjectures. Okay, and the only sort of general results that is known is a theorem of Lovász, also from the 60s, that if you don't restrict to just path or just cycles, then I can actually do this with n/2 path or cycles, except I can't control how many paths or cycles I get. Okay, so this is a very nice, very short proof, and this is essentially the best that we have. One very special case where this proves one of these conjectures is that in the path decomposition conjecture, if every vertex has odd degree, then actually Lovász's theorem proves the path decomposition conjecture for that special case, because every odd degree vertex has to be the endpoint of some path. And if you have n/2 paths or cycles, well, you need n/2 paths because every vertex needs to be the endpoint of a path. Okay, but that's really essentially it. So let's try to relax this very difficult problem. So here's a relaxation. I want a set of paths whose symmetric difference gives me this given graph. So this is relaxation. Okay, and you can also ask the same thing for the cycle decomposition. So you can ask for a cycle odd cover, but for now, we're just going to focus on the path odd cover problem. Okay, so again, you give me a graph on n vertices. I want to find the minimum number of paths that I need to oddly cover this graph, or I want the symmetric difference of the paths to be the edge set of the graph. Okay, so here's a simple example. Here's a graph. It has maximum degree 4 and it has 4 odd vertices, with the square vertices have odd degree. Okay, and you can it's not difficult to see that if you want to decompose this graph, you need at least 3 paths to decompose this. But with an odd cover, you can actually do this with 2 paths. And here's an odd cover with 2 paths. Okay, so this doubled edge here gets canceled out, right? So I have an odd cover of this graph with 2 paths. Okay, and let's make some sort of immediate observations. So again, every odd degree vertex needs to be the endpoint of some path because parities don't change when you're looking at symmetric differences. So the minimum number of paths you need needs to be at least the half of the number of odd degree vertices. Okay, and also every path can take away sort of at most 2 edges incident to a vertex. So we also get a trivial lower bound that the max degree of the graph over 2 is also a lower bound on the minimum number of paths you need. So here's a trivial lower bound. And let me just mention that we don't know an example where this is violated by more than 1. Okay, so we don't know an example where if you just add a +1 here, we don't know an example that violates this inequality. So we think it's sort of very close to this trivial lower bound, but we can't prove it. And I don't think any of us are courageous enough to state it as a conjecture, but we don't know an example. Let me mention some other sort of interesting graph theoretical facts. If I have a path odd cover of size k, then this proves that G has linear arboricity at most k. Okay, so linear arboricity is another graph theoretical parameter that people actually care about. So it's pretty widely studied. Okay, and the linear arboricity is just a minimum size of partition of the edge set into linear forest. A linear forest is just a forest where every component is a path. Okay, so how do you get this relation? Well, you just take your paths in the odd cover and just delete all the doubled edges. Then each path gives me just sort of a linear forest, right? I started with a path and I deleted some edges, so it's a linear forest. Okay, so a path odd cover gives me a linear forest decomposition. Okay, and there's another long-standing conjecture on linear arboricity that it's always at most the maximum degree of G +1 over 2. Okay, and this is still open. Okay, and what's interesting is that again, we don't know an example where the path odd cover number violates this bound. So since this is not a graph theoretic audience, I could say maybe this is an approach to proving the linear arboricity conjecture for some special cases of graphs where this term dominates the odd degree term, right? Because sometimes it's sort of easier to prove a stronger statement. Okay, but what we can prove is that, so I mean, these 2 quantities can be very far away if you have a lot of vertices of odd degree, but excluding that reason, so if the graph has all even degrees, then actually the linear arboresty and the path odd cover number are very closely connected. So in particular, we have this relation here. Okay, but I won't go into too much detail on this, but it is very closely related to the linear arboresty, at least in the cases where you have very few vertices of odd degree. Okay, so let's move on. Okay, so what do we prove? Our main result in our work is that we have a general upper bound where, again, we have this trivial lower bound of number of odd degree vertices over 2 and the max degree over 2. Okay, and what we get is that we can always find a path odd cover of size at most the maximum of the odd degree of vertices over 2, or essentially the maximum degree. So we have an extra factor of 2 here. Okay, so all we're losing is this extra factor of 2 in the maximum degree term. Okay, and let me just mention that this is sort of a dramatic improvement over the path decomposition conjecture, because this tells you that no matter how big the graph is, if you have small maximum degree, then I can just oddly cover it with just a few paths, which is generally not true even for like cubic or for regular graphs that have large degree. Okay, and this sort of dramatic improvement, which changes the dependency on the number of vertices of the maximum degree, comes from, well, the prototypical example is this example here. So let's say you have a vertex disjoint union of cycles, you have many cycles. Well, it turns out no matter how many cycles you have, I can always odd cover this with 2 paths. Okay, so here is an example of 2 paths that odd cover this union of many cycles. Okay, and to some of you, this picture might already be familiar. And this is sort of essentially the idea that was used to prove that Birkhoff polytope has diameter 2. So let me get into that a little bit. So here's the section on polytopes. So a partition polytope is, so you have n items and you want to partition these items into k clusters of fixed sizes. Okay, so I have fixed sizes for my clusters whose sizes sum up to n. Now I want to sort of put my n items into these clusters. Okay, so this fixed size partition polytope is defined in this way. So each column corresponds to an item, and each item should go into at most 1 cluster. Okay, so the sum of the variables in each column should add up to 1. Each row corresponds to a cluster, and the sum of these variables should be exactly kappa I. Okay, so there should be exactly kappa I items that are assigned to cluster I. Okay, and all the variables should be non-negative. Okay, so if all the clusters have size 1 exactly, well, it's essentially just a permutation, right? And this is the Birkhoff polytope. And it's also a special case of transportation polytopes, which was mentioned earlier yesterday. Okay, and it's well known that this constrained matrix is totally unimodular, so all the vertices are integral. Okay, and the vertices correspond exactly to the integral sort of clusterings, so assignments of the items into these K clusters. Okay, so now let's look at sort of the relation between 2 clusterings on this polytope. So let's say I take 2 clusterings of the n items. So what's the relation between these? So how do I get from cluster 1 to the second cluster? Well, I can make this thing called a clustering difference graph, where I have a vertex for each cluster, and for each item that needs to move from this cluster to a different cluster, I add a directed edge from this cluster to the other cluster. Okay, so this is a balanced directed multigraph because every cluster has fixed size. So if an item needs to leave this cluster, that means that some other item has to come in. Right, so the in degree is always equal to the out degree, and you can have parallel edges. So it's a balanced directed multigraph. Okay, and it has maximum out degree at most the size of kappa I, right? Because you have a cluster of size kappa I. At most, kappa I items can leave this cluster. Okay, and Stefan proved that actually, if you give me 2 clusters, they form an edge in this fixed size partition polytope if and only if this difference graph is just a directed cycle, just one directed cycle. So it's a nice characterization of the edges of this partition polytope. Okay, so let's see an example of this. So again, I take a vertex union of cycles. So let's say I have 6 clusters. And I have 3 pairs where I need to swap 1 item each. So I can sort of adapt the picture that I had from before, something like this. So I sort of think of this as a symmetric difference of 2 directed cycles. And is really not really the right picture. But if let's pretend that every cluster had some extra items, and I could think of this as, so this I need to move an item from cluster 1 to cluster 2. Let's say I temporarily move some other item to here, and then that gets moved back in the other in the later cycle. Okay, but if you don't have extra items, and really the right picture is something like this. Right, so I move an item from cluster 1 to 2. The item from cluster 2 gets moved to 3 temporarily, but that gets fixed and gets moved back to 1 in the next iteration. Okay, so any number of vertex between cycles like this can be decomposed into just 2 directed cycles, which means they're distance 2 away on the partition polytope. Okay, so the distance, like the edge walk distance between 2 clusterings, is exactly the minimum number of directed cycles that you need to decompose this clustering difference graph. And what we mean by decompose is really like you're allowed to use these like non-edges, which is sort of weird. But it's really what makes relates this to this odd cover problem, where we're allowed to use non-edges in the graph, and as long as we cancel them out by using them an even number of times. Okay, and since this is a circuits workshop, let me also just mention something about circuits. So we can generalize this fixed size partition polytope to a bounded size partition polytope, where again, so every item is still assigned to 1 cluster, but each cluster just has a lower bound, a fixed lower bound, and a fixed upper bound on its size. Okay, so it just the sum of all the variables in this row is just between these 2 fixed constants. Okay, it turns out in this case, turns out the edges of this polytope are not so easy to characterize. It has a characterization, but it's sort of complicated. But the circuits of this bounded size partition polytope has a very nice characterization that it's either just a directed cycle or a directed path, right? Because here the cluster sizes are not fixed, so the difference graph might not be balanced. So it's either a directed cycle or a path. Very nice characterizations. But we won't really talk about that in this talk. Okay, so let me just run through sort of a simplified version of the diameter bound for partition polytope. So this is from Stefan's work from 2013, and it's a slightly weaker statement than what he proves in the paper. Okay, so the diameter of the fixed size partition polytope is at most 2 times the maximum size of a cluster. And here's a proof. So if I take any 2 clusterings, then their difference graph is a balanced directed multigraph and has maximum in or out degree at most the maximum size of any cluster, right? Okay, here's a lemma. If I have a vertex union of directed cycles, I can sort of take these, get rid of these cycles with 2 steps, right? Just this picture is a proof. Here's the other step. If I have a balanced directed multigraph, then I can find a set of vertex disjoint cycles, directed cycles, that cover every vertex of maximum degree. Okay, so maximum in or out degree doesn't matter because it's balanced. I can always find a set of vertex disjoint cycles that cover all the max degree vertices. Okay, so before I give you the proof of this, assuming that these 2 lemmas is this upper bound on the diameter is immediate, because I'm starting with this difference graph, which is a balanced directed multigraph with maximum degree at most max of the kappas. I can reduce the max degree by 1, or maximum out degree by 1, just by finding a set of vertex disjoint cycles that hit all the max degree vertices and covering them with two cycles. Okay, I can reduce the maximum out degree by 1 with 2 cycles, which means I just need maximum kappa steps, right? And I need 2 cycles at each steps. So this gives me this upper bound on the diameter of the partition polytope. Okay, so we just need to explain why this lemma holds. Okay, so again, this lemma was proved by Stefan in his paper, but in our work, we give a new proof of this, which according to Stefan's words, it's a much nicer proof. But it's more elementary. So let me give you this proof. Okay, so what we're going to do is construct an auxiliary bipartite graph where I split every vertex into 2, which one of them sort of collects all the incoming edges, and then one of them collects all the outgoing edges. Okay, so for every arc that was in the original digraph, I add an edge from the out vertex of the tail to the in vertex of the head. Okay, and I also delete for every maximum degree vertex. I just delete this. For For every vertex that is not maximum degree, I add an edge between the two corresponding vertices. Okay, so let me just show you a picture of this. So here I start with this directed graph, balanced directed graph. I double all the vertices. I add sort of a matching between the two vertices that correspond to 1, as long as it does not have maximum degree, right? So only the vertex 1 and 7 don't have maximum degree, because maximum degree out degree is 2. So I add an edge like this, 7 and 1. And for all the arcs, let's say 3, 1, I add an edge from 3, the out part of 3 to in vertex of 1. Okay, and what I claim now is that a set of vertex distance cycles in the original graph that cover all the max degree vertices correspond exactly to the perfect matchings of this bipartite graph. Okay, and why is this? Well, let's say I take a perfect matching in this graph. Well, if I look at one vertex, it could be just matched to its partner, right? So, and if I just collapse this bipartite graph, it just means it's basically an isolated vertex. It disappears in the directed graph. Okay, but I got rid of all of those edges in the max degree vertices. Okay, so if I take a look at one of the maximum degree vertices, it cannot be matched to its partner because that edge was deleted. So it has to be matched to something else. And I look at the partner of that vertex, that has to be matched to something else, and I keep following along, and it eventually has to give me a directed cycle. Right? So if I collapse this bipartite graph, it's a balanced directed graph with maximum degree 1. So it's just a vertex disjunction of cycles. So we have this 1-to-1 correspondence between vertex disjunction of cycles that cover all the max degree vertices and the perfect matchings. So now all we have to do is prove that this bipartite graph has a perfect matching. And we just do that by checking Hall's condition, right? You start with one side, take a subset of the vertices, show that its neighborhood is at least as large, and we just count the edges. Okay, so all we have to do is verify Hall's condition in this auxiliary bipartite graph. Okay, so that proves the lemma and also proves the sort of weaker upper bound on the partition polytope diameter. Let's get back to our problem, this path odd cover problem. So I want to prove this upper bound here. So I can always find a path odd cover of size at most the maximum of the odd vertices over 2, or essentially the maximum degree. So let's first look at the special case that the graph is even. So every vertex has even degree. So let's forget the odd degree vertices for now. Okay, so again, I can find a set of vertex disjunction cycles that cover all the maximum degree vertices, because if it's even, then I can find the balanced orientation. And I just apply the directed graph lemma that I can find a set of vertex disjunction cycles that cover all the maximum degree vertices. And then I just forget the orientation. So I can find a set of vertex disjunction cycles that cover all the maximum degree vertices. And again, I can cover any set of vertex disjunction cycles with 2 paths, odd cover them with 2 paths. Okay, so I delete those. So I reduce the maximum degree by 2 with 2 paths, which means I keep going and I just need the maximum degree number of paths to odd cover my even graph. Okay, so what if the graph is not even? So it has some odd degree vertices. Well, so the first approach is to just join all the odd degree vertices by some arbitrary paths. So I can just do this greedily, and I can use V odd over 2 paths to get rid of all the odd degree vertices. The remaining graph has all even degree and has maximum degree at most the max degree of the starting graph, which I can cover by the previous argument with delta paths. So this gives an upper bound of V odd over 2 plus delta, which is not quite as good as what we want. We want a maximum, not a plus. Okay, and we just have to get rid of this plus. So the way we do that is instead of getting rid of the odd degree vertices and the max degree separately, we try to do this at the same time. Okay, so what we do is we start with an arbitrary perfect matching of the odd degree vertices, and this perfect matching doesn't have to be in the original graph. Okay, and you take the symmetric difference to make it even. And each iteration, so now that G prime is even, I can find a set of vertex disjunction cycles which cover all the max degree vertices. I can cover those with 2 paths. And we show that we can just modify these 2 paths to cover the symmetric difference with 2 additional edges in this matching. Okay, so our main technical lemma is that we can always sort of integrate or absorb 2 additional edges in our odd cover of 2 paths. And this is a technical lemma. It's just 10 pages of case analysis essentially, but that's what we did. Okay, so we essentially, so what this tells us is that we can decrease the max degree and d odd over 2 by 2 at each step. We don't have to do this separately. We can do them decrease by 2 at the same time, and that basically proves this upper bound. Okay, so cycles. You can ask the same problem for cycles. Given an even graph, how many cycles do you need to oddly cover the graph? And we don't really have much to say other than this. Our only tool that we can find a vertex in a union of cycles that cover every max degree vertex and cover those with 2 cycles. That's the best we can do. So we can do this with delta cycles. Right, and this is kind of interesting because the decomposition version, the original conjecture, is not even known that you can do this with linear number of cycles. But here we just get a nice clean upper bound of delta cycles. Okay, so it's essentially the same proof. Okay, so let me end with a couple of problems. So really our bottleneck and like really our only tool is that we can find a vertex with union of cycles that cover all the max degree vertices, and we're sort of at each step we're reducing the maximum degree. Okay, but if we do this just one step at a time, then we really need 2 paths or 2 cycles to reduce the max degree once. But what if we try to combine 2 steps at the same time? So if I give you an even graph with maximum degree 4, can you find 3 paths or 3 cycles whose symmetric difference is this graph? And if you can prove this, then this will immediately improve our upper bound on path or cycle odd covers. Okay, and maybe a more interesting question is the same question, but for the partition polytope diameter. So given a balanced directed multigraph with in or out degree at most 2, can you decompose this in the sort of the clustering difference graph sense? Can you decompose it into 3 directed cycles? Okay, so again, if you can prove this, this would immediately improve the upper bound on the partition polytope from 2 times the maximum size of a cluster to 3/2. Okay, and maybe you can even do better if you can sort of combine 3 steps with 4 cycles. You can maybe get up to 4/3, but that is essentially the best you could hope for because there is a lower bound of 4/3, the maximum size of a cluster. Okay, so I think the first step is to really just focus on this simpler problem of trying to combining 2 steps at once with 3 directed cycles. So I'll stop here. Thank you.
Thanks, Yong-Ho. Any question from the Zoom audience? What about people at present? Any questions? Yong-Ho? Yes.
Like that cluster graph, I would think it would create kind of like iterated blow up almost, like in the clusters, where it creates like this like complete cycle or complete graph based on how many clusters you have. Is there something you can exploit like with that structure? Try and
So within a cluster, you don't add any arcs because it would be like a loop because every vertex corresponds to a cluster. And each arc corresponds to an item that needs to be moved to a different cluster.
okay,
So like each cluster is really just a vertex.
right, okay, and there's no arcs between the clusters unless you're trying to move said item there.
Yes.
Okay, so you could have like a bunch of like little trees or paths of like 2 or something like that, right? And that's just what it's going to be.
In the bounded size partition polytope, yes.
Okay.
In the fixed size, it has to be balanced
Okay.
because out degree has to equal in degree. So it would just be like a union of cycles.
Maybe you said it and I missed that, but like for the fixed size partition polytope, what is the lower bound of the diameter? Like,
So the best that we know is this 4/3 the
sorry,
max.
oh.
Yeah, 4/3 the maximum size of a cluster.
Okay, so that's the lower bound and the upper bound is 2, right? That's what I
Yes.
understand. Okay.
Maybe this is already implicit in the proof that you gave, but for the odd path covering or partition, is it known whether each edge of the complete graph only needs to be taken either once or twice? Or maybe sometimes you need to take an edge 3 or 4 more times?
Not sure actually. So the bound goes from n/1 to half of n. And this is essentially tight. So I think you'll probably need to use some edges more than twice.
I'd like to comment on something. So even with this approach at the moment, the set of moves that we consider for the construction is actually still very restricted. In the framing of partition polytopes, items are at most moved twice, and they are actually only misplaced to a different cluster that they are supposed to go to for one step until they are actually moved to their genuine target. So, so some of these open problems towards the end, they could just expand the mantra of what we allow ourselves in these moves. Maybe we can get something dramatically better if we don't force ourselves to use this specific construction.
All right, let's thank Yong-Ho again.